अरे मना दिव्या, ए दिव्या.
Hello.
ना शायद वर्मा अंकल ने लॉगिन नहीं किया है।
मैं पूछने जा रहा हूँ।
मैडम मम्मा बोल रही है आप अनम्यूट हैं।
कौन?
आप।
हाँ। हेलो। सागिन हो जाइए।
अरे मैं अभी 5 मिनट में पहुंचूंगा घर।
अच्छा ठीक है।
अभी रास्ते में हूँ।
हाँ
5 मिनट में पहुंच रहा हूँ।
आप मोबाइल पे लॉगिन हो जाइए।
अच्छा हाँ ठीक है।
हाँ डॉक्टर शालिनी।
Yes, sir.
Dr. Verma will be available in 5 minutes.
Okay, sir.
Good evening, Dr. Subramanian.
Good evening, sir. How are you?
I'm fine. I'm fine. It's very good to see you.
आप लोग हुक्म कर दिया हम तो आ गया बस.
It's a great, sir. It's a great, sir.
So we are waiting
It
for
is.
somebody.
Just I was waiting for the chairman.
Oh.
He is on the way. He will be reaching in 5 minutes.
Okay.
And I'm also waiting to the participants.
Yeah, acha. Yeah, now it's about 280. You want to get them increased?
Yeah. Because your talk is very important, so others should not miss it.
Yeah. That's true. That's true.
And today, one of our speakers might be missing.
Oh, I see. In fact, I was about to ask Dr. Shalini.
Yeah, how many? Because one, if some dropout is there, at least the other people they can
Yeah,
get.
just no, son doesn't know. Just I got the message from him. Due to some unavoidable reasons, he is unable to deliver his talk today.
He is a national candidate or international candidate?
International is from Tunisia.
From Tunisia. Okay. Acha.
Dr. Isifi.
Oh, I see. He was there the first day. He was there, I think.
Pardon?
He was there on the first day. He was there. Our meeting. He was there, I think.
I am here, and I am here to get the blessing of all of you for my future career, future health, future comforts.
Thank you. You are naturally you are elder to all, so your blessings are very much needed.
Best wishes of youngers are very sincere. So today we'll be having 6 talks.
Oh, I see.
Yeah.
So all the 6 except one, everybody is confirmed.
Yeah, all 7 were confirmed.
Okay.
Just at the 11th hour, just 10 minutes before I got his message that he's finding difficult today.
I see.
I have given offer for tomorrow, if comfortable to him.
Acha,
Yeah.
the Tunisian gentleman.
So, he is from this Tunisia.
Tunisia, okay.
Yeah, Edit
He was
Research
there.
Institute.
Probably he was there the first day when we had the meeting. He was there, I think.
No, yeah, there are 2 persons from. There are 2 professors from there.
Oh, okay.
One is Muhammad Wasser, and second is the
SCP.
Okay. So Mr. Muhammad was there. Dr. Muhammad was there.
Muhammad was there.
Yes, Dr. Muhammad was there, sir.
Yeah.
Yeah, his talk is tomorrow.
I see.
Sir, today we have got how many lectures today? 7 lectures are planned. 6. Okay.
What, Ravi?
We have got 7 lectures today, but I think 1 lecture is not there. So total 6 lectures will be there, I think, today.
Yes, sir. Total 6 lectures will be there. Initially, there were 7 lectures.
Yeah.
So Professor Isifi from Tunisia will be delivering tomorrow.
Achha, he will deliver lecture tomorrow. Okay. Then tomorrow we will have 7 lectures and validatory function.
Yes,
validatory
sir.
function and 7 lectures.
Yes, sir.
By the time I think our chairman sir will.
Professor Verma has joined us. Professor Verma, can you please, sir, can you please unmute yourself? Verma, sir, can you please unmute yourself?
Yeah, unmuted.
Yes, sir. Good evening, sir.
Good evening, Shalini.
And a warm welcome to all to our chairperson, Professor Jeyakanthan Verma, to all the potential speakers and the participants. I welcome you all on the second day of the international workshop on application of remote sensing and GSI and GIS. Professor Jeyakanthan Verma.
Just a minute.
Is a chancellor, presently working as a chancellor in Rabindranath Tagore University, C.V. Raman University, and also as an advisor of ISRO group of universities. I invite you, sir, to chair today's session and invite the speakers.
Okay, good evening, everyone. I'm very happy to welcome all the speakers and delegates, participants in this very crucial session of second day. And to start with, we have Dr. S.K. Subramanian, former scientist G and Group Director, NRSC, ISRO Department of Space, Hyderabad, India. He is going to talk on relevance of remote sensing and GIS technology in river rejuvenation. This is a very, very important topic. 1/3 of world's 246 longest rivers are facing the water shortages. 3 major rivers in India also like Kaveri, Krishna and Godavari. In last survey, it has been reported that they are short of water by almost about 30%. There are many rivers which have gone is extinct in wake of the pollution and other climate changes, and it will be very interesting topic and very relevant for the society and human beings and environment. I welcome Dr. S.K. Subramanian to deliver his lecture.
Before that, sir, if you permit, I would like to give a brief introduction of Dr. S.K. Subramanian, sir, because it would be injustice if we all doesn't know about his achievements and the awards. All the speakers here are really great. They have done a great job. They are all awardees of the different national and the international awards and have published really a very good research papers which highlights students, the research scholars and the working professionals. So Dr. Subramanian has 36 years of professional experience in the field of remote sensing, geomorphology and groundwater, and he has coordinated a number of national mission projects including Integrated Mission for Sustainable Development, National Resources Information System, National Agricultural Technology Project and many international projects. He was Scientist G and Group Director, Hydrology Group at National Remote Sensing Center, Indian Space Research Organization, Department of Space. He was also the National Project Coordinator and executed many projects for the Government of India, including the Rajiv Gandhi National Drinking Water Mission, which we all know was a very important mission during its tenure. He also served as a member, high-level committee on the on different National Drinking Water Sanitation Council, Government of India, in the area of hydrology, use of satellite data, high-end technology and drinking water security. He was also a Mackenzie Chair Professor of DST, Government of India at Institute of Remote Sensing, and presently he is serving and rendering his services at Art of Living, Bangalore in River Rejuvenation Project as an advisor. I welcome you, sir, to please deliver your talk. Dr. Subramanian, sir.
Yeah, yes. Am I audible?
Yes, sir.
Yeah. First of all, I thank chairman of this session, and also I thank Dr. Shalini for giving me about what are all I have just done for the past 30-35 years of service. And luckily, I'm really thankful to the Almighty. All through, I was just working in my specialist area only. that is the geomorphology and also the groundwater. So yesterday, many people just talked about all the technology. What is GIS? What is remote sensing technology, and also what GIS, and what are all the technical improvements that are just available right from the initial stage up till date. But today, I'll be just talking mostly about what the technology can contribute to the society. So my talk mostly will be on the applied aspect of the technology, how it will be useful to the society, and how it has really it has really served its purpose with respect to some of the societies. I'll be just taking only one example, how the technology it has really contributed for the society. So with this prelude, so let me just go about the present day here. See, we live in two worlds, very well. One is the natural world, which was there in the initial stage and all. When the population just grows and there are so many developments, in the name of the developments, we have completely lost, rather we are just going against the nature, and we are completely on the constructed world. So when we just take about the natural world and then the constructed world, one is the self-regulating mechanism. When you just talk about the natural world, it has got the self-regulating mechanism. But whereas in case of the constructed world, we are to manage the whole this thing. So that's how these are both in case of the natural world and then the constructed world. These both are increasingly in conflict. And when you talk about the framework for understanding and managing the earth, we can just say, for example, if we just talk about any knowledge, so in case of the geographical knowledge, we have to plan, we have to manage, we have to act in case of any development. So by what? By creating, or we can just say we have to just measure some of the development, or organize the plan, analyze it, model it. So that's how we just put the technology into different categories. And the technology should be holistic, it should be comprehensive, it should be systematic, analytic, and also the visual. So that is how we are just taking, see, all this parameter, whatever we have just indicated here, most of the parameter, or almost all the parameters, the remote sensing and also the GIS, it takes care of it. So that's why it is a very integrated technology. When we just talk about the integrated technology, see, any technology, if we just talk about any technology, we have to have certain leaders. See, in case of remote sensing technology, in case of the Department of Space, the father of the space, Vikram Sarabhai, he used to just tell, we are convinced that we have to play a meaningful role nationally and also in the community of nations, that is internationally, and we should be second to none. So technology wise, we should be at par with all the developed countries, but the technology is, it should just face the real problems of the man and society. So what means, whatever the technology we are just having, it should be a high-end technology and we should be at par with the developed countries. But the technology, it should not be only with respect to the status, it should also face the problems, the real problems, and solve the common man. So that's how the technology, space technology, even though we just talked about the rocket science and other this thing, when it comes to the ground level, we also address the common man. That's how the remote sensing, actually Department of Space has just contributed so much in the form of project to many common man. So the technology, it should be put into the use in the ground. So for that, See, all the scientists and technologists, they cannot just go to the ground for all the people and all. So that's how the spiritual leaders or the NGOs or some of the societal leaders, they play an important role. In case of the present day, rather you can just say the topic which I am going to present now, the Art of Living, the founder, in fact, His Holiness Ravi Shankar, his team has just developed, because he got a wonderful volunteer, not only in India, he has got about 150 countries, they have got a volunteers. So they just take many projects which is useful for the society. In this case, we have just taken, I will just take one example from Tamil Nadu, what they have just done with respect to the society using the remote sensing and the GIS technology. You know very well, yesterday also we have just seen what remote sensing can just do, the applications with respect to remote sensing. We can just say it is contributed a lot in agriculture, forestry, water resources, ocean, rural development, urban development, and there are so many, the list goes on. And also, when you talk about the users, they are all from the government agencies, or it can be from the private agencies, and also the NGOs. And ultimately, what happened, it just goes into the societal benefit. So that's how you can just see the technology. What is the technology application? You have to just know about the application, what it can just do for the particular ministry or particular the private sector or the NGO or the academia or university. So when you talk about the, in fact, previously what happened, we used to just tell the remote sensing and GIS, but now since the technology is just being upgraded year by year, day by day, the remote sensing and then the GIS technology comes under the umbrella of geospatial information. So that's how the geospatial information, it talks about the global positioning system, that is GPS, which is the system of Earth orbiting satellite, which can provide precise information. Yesterday also we just talked about the location, how far it is just precise, and the remote sensing with respect to the satellite, what the satellite information it can just give, the aircraft, and nowadays drones are also playing an important role to capture the information about the Earth surface. And all the information, initially it was there in the hard copy, but now you know it is the digital world, and everything now it is in the form of a digital form, where you can just have the accurate information on the digital photos or images, and any other information, and all it is in the digital form. And when you talk about all this thing, you have to have analyze, or systematically you just put everything in order, where you have this software system which is capable of having the input, taking the input, the storage, manipulation, analysis, and put everything in the form of output in a spatial information. All those things, it is coming under the spatial with the location accuracy. So what is the beauty of this technology? If we just take some other technology or some other information, it will just give only a very few, or you can just say the narrow path. But whereas in case of the GIS, it provides the various of information. See, like we can just say the topology, you can just see the images, you can just put the CAD drawings, you can annotate it, you can just put the observe in the 3D objects, many things. We all put it in the attribute or in the tabular form. All this, they can be integrated. They can just put under the one umbrella. So over here, when you talk about the geospatial information, you can just talk about you can just put the information on the roads, the land parcel. See what we are the conference. It just talks about the water, land, energy, and also the society. So all this information, roads, land parcel, population, utilities, in case of the groundwater, the well information, sanitation, and so on. All the information you can just put under one umbrella, and you can just see the whatever the information you just want, you can filter it and then just see as per your interest. So what is the context and then the content? See, the information, it can just go from the local to global, or sometimes we can just say reverse global to local also. So in case, if you want to just talk about the local to global, we try to just attack the problem watershed wise. See, because why we are just taking watershed? Watershed is a natural boundary. So that's how we can use the whatever the technological or whatever the scientific information, you should just go on the natural boundary, mostly on the watershed basis. And also the communities see the neighborhood, how it is just happening and how the whole thing it is just percolated, and the district. So district as an administrative unit. So once you have that information, you can just see the pattern, and you can linkage with the other part of the country also. Try to see the trend, so that the whole thing, the whole technology, we can just go from the local to the global, or other way, the global to local also. So that is the beauty of this technology. So another thing, whatever the information you just want to just have it real time, you can just have it. For example, you can just say this first picture, it just gives the 19th December, how is the irrigation potential or irrigation of particular area. So in 3rd November, you can just say the blue tinge, wherever the blue tinge it is just there, those area it has been irrigated. And when you talk about the within 9 days or within 10 days, the tinge, the blue tinge, it is just getting increased. So the irrigation potential or the irrigation area where it is just been gone to till the end of the canal, and what are all the area it has been just irrigated, and what is the intensity of the irrigation also, you can just come to know about this technology. Apart from that, you can just see about the health of the canal also, because of course I have not just put the slide. The health of the canal, how much water it is just going, it is just going 3/4 of the canal, or it is only 1/4 of the canal, whether the water has reached to the tail end of the canal. All this information in a real time, you can able to assess it. Okay, that is with respect to the surface water, because of the constraint of the time, I am not just going, I am not elaborating it. I am just giving only what the technology can just do with respect to the water sector. The similar way, of course, there are many things with respect to the tank, health of the tank, we can just see, and we can talk about the reservoir. There are many aspects with respect to the surface water. The similar way, many people will be just thinking what remote sensing can just do underground information. So because the groundwater, it is only the underground information. So the underground information, the geologists and the geomorphologists, they can able to pick out some of the indirect information, like you can just see the cracks on the surface of the earth, which we call as a fault. So what is the fault, and how the nature of the fault, how the fault is it is just behaving on the ground, and what is its direction. Everything we can able to find out from this image. For example, in this image, you are able to see some of the linear features and all. So that red linear features, they are all the fault, where along the fault we have the vegetation. So that's how we can able to just say this is the groundwater, the surface and underground surface, it just flows over there. That is a base flow, what we call. So this is the carrier. But some of the information, you can just say the linear information, that is the black one, that is the dike, what we call, that is it is just like a wall, it is a barrier. So we can try to find out where is the barrier and where is the carrier of the groundwater, and accordingly we will just give some of the potential or the prospect. I would like to just say over here, I was the national coordinator. I was the national director for the national groundwater mission. Previously, it was called as Rajiv Gandhi National Drinking Water Mission, where the entire country, we have mapped the groundwater prospects for the entire India, including Lakshadweep and also the Andaman Nicobars. So this information, so based on this information, of course, it is not only ISRO or NRSC, the partners, they're all, it has all been done by all the remote sensing centers, some of the universities, and also some of one or two private agencies and all. So that's how this information we could able to develop. It took about 15 years for the entire country. Now the information is available. It just took about 15 years. So now that information is available in the form of the groundwater prospect map. So here, this is what the information we have just developed for the entire country, just for the benefit of the participants. You can just see the color of all those things. Because this got all, there are about 25 layers of information. It is available in this map. So if you want to just talk about this map, it needs almost about 1 or 2 hours. I just want to just emphasize that all the information using the GIS and then using the remote sensing and GIS technology, we have abbreviated or aggregated the whole this thing into one form as a map. And for the people, those who are not familiar with the technology, the color scheme we have just given. For example, if you just give from violet to red, it just gives that information regarding violet is the very good groundwater potential. Red is almost nil, dry groundwater potential. So that's how the information it is just developed on 1:50,000 for entire country. Now the information is available with the Bhuvan and the Jal Shakti Ministry also. For example, if you just go now, previously it was there with NRSC, and now this information is now with the National Water Informatics Center. It is a part of Jal Shakti Ministry. So you can download all that information from this Bhuvan portal, and the people, those who are working in this field, they need not just go to all that information what I just told about 23 layers of information. You don't start the work from the scratch. You take that information from the middle level, try to put you add your value added your information, so that whatever the information you just want as per your need, the whole thing can be just developed and it can just go for the society. And one is with respect to India, and some of the information, for example, the contours over here, we cannot just put it in the open domain as per the map policy. So you can take it from the information available on the global or international level, try to put that information together so that you can just get the height information also wherever you want to just do the work. So this is how we have just taken. First, you just take the natural boundary of a particular watershed, like the chairman was just telling about the Kaveri. You just take the Kaveri basin. The Kaveri basin, it has got many watershed. Take that watershed, which is having a large area, and from that watershed, you try to just put the mini watershed, or you can just say the watershed. Of course, you know, when you just talk about the classification of watershed, there are many categories. It has been already scientifically, it has been further divided into so many classes. And we just try to come the finest one, that is the micro watershed. So the micro watershed, you just put all that information, what I was just telling you, geology, geomorphology, slope, land use, and so many. All those things we can just put and get an integrated map. And that's how we have just developed for the micro watershed. And along the micro watershed, you can just see what are all the area which has got the groundwater potential, which I have already just showed. And to keep the groundwater potential, you should make the sustainability. how to make the sustainability, you have to just have some of the groundwater, rather recharging structures and all, so that the underground aquifers, it always just have a saturated condition. So that's how we try to find out, rather try to locate all that information where the groundwater, where the water recharge structures can be just put, and this we just give it to the people, those who are working in the field. So this is how, that is one thing is manually you can just do. Otherwise, like yesterday, somebody was just talking about of course, today they are going to talk about the machine learning and all, what you call as artificial intelligence. When you talk about the artificial intelligence, what you have to do is you just train the machine with so many criteria. For example, if you want to just go for an Nalaban, you try to just give where the Nalaban should be, which order of the stream the Nalaban should be, and how you have to just take it, what are all the other criteria to locate the Nalaban or the water harvesting structures and all. So automatically the machine will identify so many locations. From there you can able to just filter which is the possible location where you can just go for water harvesting structures and all. So this is how we have, of course, now I'll just come to the area what we are using this technology. We have put the whole the project output in the district called Vellore in Tamil Nadu. So this is how you can just see the boulder check, and we have not just taken many. We have just taken only a few, depending upon the budget and depending upon the government, rather the district administration's need. So we have just given only 3-4 recommendations. One is a boulder check, recharge or the injection well. So once you have the recharge well, it just gives it recharges the shallow aquifer. When you have the deep water table, then you have to go for the injection well and all. And some of the area where the desilting of the tank has also been just done. So all these things we have used the remote sensing technology. Also, we have also added, rather we have put the internet mapping in the technology. That means using the Google Earth and Google My Map. Because the execution people, rather the volunteers, they are very familiar with only the mobile phone and then the Google Earth, rather you can just say Google image. So that is so based on their convenience, we have put all the information using the internet mapping technology, using the Google Earth, and try to just give all the information with respect to the coordinates. So once this information it is just given, of course, I got another 5 minutes time.
Yeah.
Okay, thank you. So try to just give all the information in the form of questionnaires. Go to the particular field. What is the watershed? What is the village? What are all the people over there? What is the borewell? It is there, everything. So all these things, it is in the form of questionnaire. The volunteers of Art of Living volunteers, they have just taken all that information, and this information is all the ones that data it is just collected, it is fed into the headquarters in Bangalore. So here you can just see you have the interaction between the field staff, also the GIS person who is just working in Bangalore. So we have the interaction on real time, and apart from that, we have the geotagging also for each and every water harvesting structure. What is the length of the water harvesting structure, when it is just done, overall it is just done, whole thing it is just available. So what we are just doing over here, along with the remote sensing technology and then the GIS technology, we have also added the mobile technology, and you can update the data also. For example, if you are somebody, you want to just add some more information on that fund, we can update the data. So all information, it is just available on the database. So this is how you can just see the people, they have just taken the Google Earth image and then identified all those things. And regarding all that information, it is mainly for the people, rather we can just say the district administration, they want to know about the entire information of each and every water harvesting structures. So this is how the Naga Nadi, you can just say it is a part of Kaveri Basin, and you are just seeing a small watershed over there that is called the Naga Nadi watershed, which is the micro watershed which is in Tamil Nadu. So this has got, of course, I do not want to just go about the details. So this is how the whole thing it is. Just then the impact after completing all that work, you can just see the impact of the wells over there. You can just see the one which is on the, so this one. This is all, it is, I think probably it is on 2015 or so, but 18 and 19, we can just see how the impact of the watershed, it is the water table, it has increased. You can able to just see. So you can just see in the field. This is what it was there previously. And after doing all those things, how the water table, it has just increased. A dry well, which has come up to this level, and even it has just come almost up to the surface level as on 29th of November. These are all we have just taken from the field. So whole this thing, for example, the district administration, the collector wanted to have the impact analysis, not from our field staff. He has identified, rather he has just given that work to the Tamil Nadu Water and the Drainage Board. So that is a government agency. The government agency has undertaken the survey for the entire watershed, and then they just come out with the fact it has the table, the water table, it has increased almost up to 5 to 6 meter level and all that places. So based on that, the next district, that is what we call the Tiruvallur, that is the adjacent to Chennai, that district collector also wanted, okay, our district also, you should just do that work. So that is how the people, our volunteers, they just started just doing some of the work over here. And you can just see what are all the, how many panchayat and what are all the watersheds and all. And here I want to just emphasize over here, you can just see the black one, how the, what is the total depth of the well, and what is the increase in the water table, it has just changed. And the red one, it is the next watershed where we have not done any water, where all the wells are dried. So this is how the Naga Nadi, it was there in 2013. And in 2015 onwards, every year you are able to just see the flow of Naga Nadi. So the whole thing, it is increased because of the aquifer, the groundwater aquifer, it has all become saturated. Automatically, the base flow, it is getting become shallower and shallower, and you also just see the surface water. So apart from that, you can just see the most of the work, it is all done by the ladies. There was no, it is all by women only. No, there was no men involved over here. So that's how the women empowerment also, it has just got one bird, one shot in two birds. And the district administration, they have just done a wonderful work on the women empowerment also. So this is the national daily, it has just given. Tamil Nadu also bagged the award very recently. It's about 10 days back the award under the best district category in the south. Vellore and Karur districts were awarded first and second spot respectively under the revival of river subcategory. So we have, for this work, we have got the best award, the first award, the first category for the entire nation. So that is how you can just see the GIS, it rapidly evolving as a project which is integrated. It is also a system, it is coordinated, it evolves as a network, it is cooperative, and also it is evolved as the collaborative, which is of societal benefits. So this is how you can just see the geographic knowledge. It is both the inventory plus the execution. It goes to the citizen. It is all going upward and downward. You can just say it is interactive with citizen, and then the geographic knowledge and the whole this thing, the information, it can just go to the global level or in the world level. And plus the information, it has to be on rather we can just say the development of the technology, it has to be on the day-to-day, or you can just say you have to update it frequently. See, that is how we can just see the decision support system, and then the automation are coming into the picture nowadays, apart from the remote sensing and then the GIS. With
Can
this,
we wind up?
yeah, with this, I thank the organizers for giving me the opportunity to just share my experience. Thank you.
Thank you, Dr. Subramanian. You covered a very interesting topic in a very interesting manner, integrating societal participation and how the remote sensing and the technology has become now global, which can be used locally. And you gave some example of how some reservoirs were rejuvenated, and river Bagmati was rejuvenated as a sample case. Thank you very much for an interesting and informative talk,
Thank you very
Dr.
much.
Subramanian. Now, Shalini, is there some questions? One odd question we can take up.
There are no questions. In fact, everyone has appreciated for his nice presentation and his work done for the society. We all thank you, Subramanian sir, for your excellent work done by you and your team on the groundwater, on the study of the groundwater potential for the entire country. I'm sure that the professionals and the research scholars will definitely enrich their knowledge from your data and the work carried by you. It has given definitely a very good linkages how to link the technology with the society. Thank you very much, sir.
Thank you. Thank you for giving me the opportunity.
Now, next speaker will be Dr. J.V. Tyagi, Director, National Institute of Hydrology, Roorkee.
No, sir. Next is, I hope, Dr. V.S. Jeyakanthan is the next speaker.
Actually, Dr. Tyagi is not available today. So, Dr. Jeyakanthan will present that presentation.
Yes.
Dr. Tyagi.
Dr. Jeyakanthan is a scientist in the National Institute of Hydrology, Regional Center, Kakinada. And his area, he has done a wide research in the area of remote sensing and GIS, and many papers for in the national and the international journals goes to his credit.
Am I audible, madam?
Yes,
yeah, welcome, Dr. Jeyakanthan. This is a very interesting topic, remote sensing and GIS and reservoir sedimentation assessment. Actually, the last report says that almost about 200% over and above designed sedimentation, there is a inflow of sediments almost about more than 200% on average in all reservoir, which is resulting in very crucial problem for the water. So yeah. I now invite Professor Jeyakanthan to deliver a very interesting lecture on remote sensing and GIS and reservoir sedimentation assessment.
Good evening and good morning to the participants, those who are outside of India. First of all, I like to thank the organizers of this international workshop for selecting me to give a lecture or a presentation on this topic on application of remote sensing and in reservoir sedimentation assessment. I also thank our director, Dr. J.V. Tyagi for selecting me to deliver a lecture on this topic. So this slide shows about the global and Indian scenario of sedimentations that is taking place in India and all over the world. The global scenario shows that around 2 into 10 to the power of 10 tons of sedimentation is taking place per year all over the world. Whereas in the Indian rivers that carries a sediment of 6 into 10 to the power of 9 tons per year. The average soil erosion rate in India is 16.35 tons per hectare per year. Out of these, 29% is lost to the sea, and around 10% of these sediments are getting deposited into the reservoirs, where we are going to concentrate on this one. So these 10% of sedimentation is taking place in the reservoirs, and this because of this, the water storage capacity or the water holding capacity of the reservoir is getting reduced. Out of this, 61% are dislocated from one place to another. That is, the sedimentation is taking place in the catchment area. Some of them get deposited in the catchment area itself, or some of them will get deposited in the rivers and other places. The sedimentation rate in Indian reservoir ranges from 0.3 to 27 per 100 kilometers square per year. The annual capacity loss of Indian reservoirs is in the range of 0.04 to 3.34%. This is based on around 144 reservoir studies carried out by the organization known as Central Water Commission of India. And NIH, the National Institute of Hydrology, also carried out around 15 reservoirs in these studies. So all this, the erosion that is taking place in the catchment area or that is getting deposited into the reservoirs. So because of this sedimentation, the storage capacity, the water holding capacity of the reservoir reduces. So the reservoir is constructed not only to store the water, it is also known as the multi-purpose reservoirs, which is used for urban usage, irrigation purposes, for power generation, for industrial purposes, or industrial needs, or for aquaculture, etc. So when the capacity of the reservoir reduces, the usage for all these purposes, that is the water is given for urban purposes, the water that is supplied for the urban area from the reservoirs get reduced. And for the irrigation purposes also, say at the beginning of the reservoir can irrigate up to, say, for example, I am telling 10,000 hectares of reservoir, 10,000 hectares of areas. Say for after sedimentation, it gets reduced. So we should know that what is the rate of sedimentation that is taking place in the reservoir. That is the main purpose for we have to do or estimate the amount of sedimentation in the reservoir. So how we have to carry out these sedimentations? So there are two different approaches that is known as conventional approach and the remote sensing techniques. In the conventional approach, we use the hydrographic survey, or it is also known as echo sound depthing. But when you are using the conventional method, it is time consuming, it requires skilled laborers, it is costly, and inaccessible areas. We cannot go to some of the areas or some of the reservoirs are inaccessible. So we cannot go for these ground-based surveys when you are using this conventional approach. In this conventional approach, we have to use the echo sounding or boards and all. So it should be the one of the main criteria in when you are doing the echo sounding depth is the reservoir should be at least at the full reservoir level. So we have to wait up to the reservoir get filled up. Then only we can carry out these echo sounding surveys. Then there are a lot of it depends upon the skilled laborers, not only a few laborers. It requires many more laborers who's operating the boards, who's operating the different instruments, all this like this. Then after taking the surveys, it requires minimum 6 to 8 months to analyze the data of a reservoir. If the reservoir is very large one, then it takes a lot of times to carry out the reservoir. The Nagarjuna Sagar Reservoir in Andhra Pradesh, CWC has carried out around 1 year of study to carry out this survey when they are using the conventional type. So such type of long time, more time is required when we are going for the conventional type. Whereas for this, it is the replication to this conventional type is known as the remote sensing technology, remote sensing methodology. Whereas you take the satellite data from the satellite flows over the reservoirs and all over the places, all over the place on the earth surface. Whenever it flows over the reservoirs, it takes the pictures, and these pictures can be utilized to analyze, and we have to estimate that we can estimate the what is the capacity of the reservoir, and in turn we can estimate the amount of sediment that is taking place in the reservoir. So this is that is the main advantage of when you are using the remote sensing technique. When you are using the remote sensing technique, it is very cheap. We can convenient. You can sit in your lab or sit in your room, and you can. It is fast also. You can do it in a short period of time. Even within 15 days, one reservoir sedimentation study can be carried out. So the remote sensing technique is more advantageous than the conventional methodology. Hence, nowadays in India, most of the reservoir sedimentation is carried out using remote sensing techniques. So I will directly go into the, we have carried out reservoir sedimentation study recently in the Hirakud Reservoir. There I have applied it, both the optic data as well as the microwave data also. So I will emphasize, or I will explain that how we can calculate or estimate the sedimentation using optic data as well as the microwave data. When we are using the optic data, here in this study, I have used the per pixel classification approach as well as the subpixel classification approaches. And in the microwave data also we have used. So I will explain that in detail, step by step, how the sedimentation in a reservoir is estimated. So this is the study reservoir. This is known as the Hirakud Reservoir. This is the world's longest earthen dam in India. World's earthen dam. It's about 26 kilometers in length, and this project was completed during 1957. The Hirakud Reservoir has a catchment area of 83,395 kilometers square, and the live storage capacity was 5,818 million cubic meter, whereas the grass storage capacity was 8,105 million cubic meter at the FRL 192.202 meters, and the water spread area at the FRL was 743 square kilometer. This is during the period. This data or these statistics are during the period 1957. So let me explain that how a reservoir sedimentation is carried out using a per pixel classification approach. So this is the general methodology. First, we have to methodology for estimation of reservoir sedimentation. Select the appropriate reservoir water levels. The first step is to select the appropriate reservoir water levels, multi-date. Then the next step is multi-date, multispectral data, selection of multi-date, multispectral data. Then from the selected data, we have to estimate the water spread area. This water spread area is estimated using different techniques. From the estimated water spread area, we have to calculate the volume of the reservoir at different places, at different elevations or different water levels. From this, the reservoir capacity is calculated. Then From any two capacity survey, it reveals the sediment deposited in a reservoir. That is, say I am calculating the capacity of a reservoir 2020, that is for this year. Say I am, then I know what is the capacity of the reservoir during 2000. So by these two capacities gives the amount of sedimentation that is taking place in the reservoir. That is, during the 20 years of operation of the reservoir, naturally some amount of sedimentation might have been taken place in the reservoir. So during the 20,000, what is the capacity of the reservoir during 2000, and what is the capacity of the reservoir during 2020, that is after a period of 20 years or 10 years. The difference between these two capacity gives the amount of sediment that is get deposited into the reservoir. So this is the general methodology. I will go by step how we can calculate the sedimentation in a reservoir. So first we are selecting a reservoir. Then what are all the data requires for to carry out this study? First we should have a daily reservoir water level for the selected year. Daily reservoir water level for the selected years. And from, say, if you are selecting the year, say you have selected 2010, not only 1 year data you should not collect it, you have to collect at least 2 years prior to that and 2 years after to that. That is, say if you are selecting a reservoir 2010, you have to minimum 2007 to 2012 or 2013 daily reservoir water level data is required. These data, water level data can be collected from the dam authorities. They are daily monitoring the water levels, and these are recorded. From these recorded documents, we can collect the daily reservoir water levels. Then the other data requirement is contour map of the reservoir at different water levels and at the time of impoundment. That is, the contour map is nothing but the water spread area at the FRL and at different water levels. These are surveyed when the reservoir is constructed or at the time of impoundment. This is also one of the important requirement to estimate the sedimentation. Then the impoundment elevation area capacity table. This elevation area capacity table have, that is at each and every water level, what is the area, what is the water spread area, and for each and every water level, what is the capacity in the reservoir. So this document is also available with the dam authority. This is also required. Revised elevation area capacity table. If the revised elevation, if there is any revised capacity is carried out, that information is also required. Then the full reservoir level, minimum water level, bed level, these data are required. Then if there is any reports available, the reports available regarding the reservoir, that data is also required. Is this screen is visible, madam?
You can take about 2-3 minutes.
Sharing the screen. Stop sharing. Sir, this I have put one. This or otherwise I will put again.
You can take 2-3 minutes more to complete your presentation.
Your screen sharing is there is a graph? Is it visible? Is there is a
yes,
graph?
sir, it is visible, sir.
Yeah, visible.
Okay. So after collecting the daily reservoir level, so we have to construct a graph like this. This is very important. So this is important to select the period of the study. So this, whenever in the case of our Indian reservoirs, the monsoon period starts from June to October or sometimes in November also. So from the data, we can see that the reservoir water level reaches the FRL during during November, and slowly it's getting reduced. It's slowly this is the water level, and slowly it's getting reduced to its MDL. This is the Hirakud reservoir. This is the minimum drawdown level, and this is the full reservoir level. The full reservoir level is 192.02 meters, and whereas the MDLL is 179.83 meters. So this is the operating level of the reservoirs. Mostly the Indian reservoirs get operated in the live storage capacity of the reservoir. This is known as the live storage capacity. That is the water level from the minimum drawdown level to the full reservoir is known as the live storage capacity of the reservoir. In remote sensing, we can calculate, we can estimate the amount of sedimentation that is taken place in the live storage capacity of the reservoir. Why? Because this is the operating level of the reservoir. Hirakud reservoir is at the level, full reservoir level is 192.02 meters, and this is reached 191.92 during the period December 2012. So after that, it is slowly getting reduced, and even it's not reaching the water level is not reaching the minimum drawdown level during June. This is reached during the June period. So at the June, monsoon has started. So so the water level is gradually reducing. So this is a period which one we have to select. Say it may be from the full reservoir level to the MDLL level, or from the MDLL to the FRL level. Whereas in the decreasing level, when the water level is decreasing, it takes a little bit of time. But whereas when it is increasing level, it is in a very short period of time. That is from July to August. So we have to select this. I am showing that to select the period, which period we have to select. So by this, by putting like this graph, by drawing the graph like this, we have to select the appropriate period. Say in this case, even it has not touched the MDLL level. So if you select this year or this period, we cannot estimate the sedimentation up to the MDLL level. So it is better to select the period from full reservoir level to MDL. So that is from that we have to select the adequate number of satellite passes. That is at least for a minimum 1 meter level, we have to select the different water levels. First, we have to select the water levels from that period. Then make sure the selected scenes are occupied in a single path and row. Say from the satellite data, we have to select the scenes. Is it visible, madam? I think it is visible. This
Visible, sir.
Cartosat is. So if you are, we have to when we are selecting the satellite data, we should be careful that at least in one scene, all the water spread area of the reservoir is occupied in only one scene. See here, I have selected a Cartosat 1, which is having a 2.5 meter resolution. When I am using the 2.5 meter resolution of Hirakud reservoir, it is not occupied in a single scene. So it is occupied in different scenes. So this data we cannot use it. Why? Because the satellite has flown over this area during 4th December 2018, and whereas this scene comes on 4th March 2018. All these two different dates of different water levels. Hence, we cannot select them at a single water level. The whole scene has to be covered. Get the satellite data in such a way that for that particular water level on the date, the full water spread area should be covered. So I am showing this that because this is the different the Hirakud reservoir is captured in different scenes. So we could not select like this. At a water level, the water spread area should be fully covered in a single scene. That is the main purpose of showing this one. Then the third step is we should know the details of the what is the spatial resolution of the satellite data we are selecting, and the spectral resolution and radiometric resolution. The spatial resolution is for the Indian remote sensing satellite data. For example, I am telling that resource sat, it is having a 5-meter resolution, 24-meter resolution, and 56-meter resolution. For the Sentinel data, then we are having 10-meter resolution, and Landsat we are having 30-meter resolution. While selecting the satellite data, we should know what is the spatial resolution of the satellite data. Then again, we are having the spectral resolutions, spectral for each and every data, this range. Say it is, if it is, if the radiometric resolution is in the range of 2 to the power of 10, then the maximum level is this 4096 is the maximum DN value of that satellite data. If the radiometric resolution is 12 bits, then it will have a maximum DN value of 16,384. So like that, we should know these are the 3 important things when you are selecting the satellite data. That is the spatial resolution, spectral resolution, and radiometric resolution. So if you are satisfied with all these things, then you have to go to the next step. Say if in any case you are not satisfied, say your period is not first year period is not selected, then you have to go to the first step. Again, you have to carry out all these things until you are satisfied. Then only you have to go to the next step. The next step is estimation of water spread area. The water spread area is estimated using different. This is the main purpose. From the selected or purchased satellite data, we have to estimate the water spread area. The water spread area is estimated in different methodologies. It is known as band threshold approach, or classification approach, or normalized different water index, then modified normalized different water index. So these are all there. So when we are using them, different satellite data, it's having different bands, and we have to use them. For in the case of when you are using normalized different water index, it is the formula is used, that is green minus NIR, that is divided by green plus NIR. So the green band having the wavelength of 0.6 to 0.6, whereas the near infrared band having the value of 0.7 to 0.9. This is the reason, that's why I told that in the last step, we should know what is the spectral resolution, spatial resolution, and radiometric resolutions of the data. Because when you are using the formula, then which band we have to use. This information one should know it. These information can be carried out, say when you are using the Landsat data, it is having the manual, it is having what are all the different data or different bands are used. It is spectral resolution. So all these details. So here I am using the green band. So if I am using this formula normal NDWI, you can use the green band. So it is the green band is having a resolution of this band we have to use. When you are using the Landsat data, we have to use the green band, which is having a spectral resolution of 0.3 to 0.9. Then the NIR band, that is the near infrared band. Near infrared here in the Landsat data, the NIR band is having this spectral resolution of 0.85 to 0.8. So like this, when you are purchasing the data, you should know about the characteristics of the data.
Could you speed up? We are already running out of time.
Yeah. So this is then the next step is to calculate the volume of the reservoir. Say we have purchased the satellite data. From that, in the above methodology, we have estimated the water spread area. That is for the water level, for these different water levels, say for H1, H2, H5, we have purchased the water satellite data at different water levels, and we have estimated the water spread area. From the estimated water spread area, the next step is to calculate the volume between two different elevation. That is from H1 to H2, what is the volume? So like that, we have to calculate what is the volume of water occupied in the reservoir at these two elevations. Like that, we using this formula. This is the Prismoidal formula. Say for the water level H1, the water spread area occupied is A1. For the level H2, the water spread area occupied is A2. So like this, we have to estimate the volume between all the water levels from the bed level to the FRL level. We have to calculate the volume at different water levels. So first we have to calculate the V1 using this formula. Then when the water level is H1, your water spread, the estimated water spread area from the satellite data is A1. When we are having the water level H2, the water spread area is A2. So with this formula, we can calculate the volume at V1. Then we have to calculate the volume V2, V3 like that. We have to calculate, and you add up all these V1, V2, V3. Then we will get the what is the cumulative storage capacity of the reservoir. So then reservoir cumulative capacity, you add all these V1, V2, V3, etc. Then we have to calculate then we will get what is the cumulative capacity of the reservoir. With this cumulative capacity, say I have calculated the cumulative capacity of the reservoir during 2020, then I will be just minus or the difference between the capacity of the reservoir during 2000, it will give the amount of sediment that is deposited in the reservoir. So for example, for 2020, the capacity of the reservoir is 100 million meter cube. During 2000, the capacity was say 120 million meter cube. The difference between these two capacity gives us the sedimentation, that is 20 million meter cube of sedimentation is taking place in the reservoir. So this is the methodology how we are estimating the sediment in a reservoir using satellite data. So I will just speed up. Then these are all the this is the selected satellite data. I have selected the satellite was during 7th December 17. At the time, the water level was 191.93, and the estimate, this map shows the estimated water spread area. Estimated water spread area during this date and this water level was 565.9 million meter. 9 million meter square. Like this, I have selected different water levels, and I have downloaded that or purchased the data, and we have estimated what is the water spread area at different water levels. So these are all the maps it is showing, and this is one GIF file. And from this, say this is the downloaded or purchased satellite data of different Sentinel-1, Sentinel-2A for the date 7th and the water level, corresponding water level. And this is the estimated water spread area in hectares. So just I am putting all these tables. Then I am calculating what is the volume at this FRL. The volume at the volume at FRL, that is 192.02 meter, was 4,447.08 million meter cube. That is during 2017, the volume of Hirakud reservoir was 4,447.08 million meter cube. So just during during the impoundment of the survey, the capacity of the Hirakud reservoir was 5,526.5 million meter cube. So just during the operation of these 61 or 62 years of the reservoir, we have found out the yearly live storage capacity loss was 22.6 million meter cube per year. Per year in the Hirakud reservoir, a loss of 22.6 million meter cube of sedimentation is taking place. So these are all the other calculations like reduction live storage in hectare meter and the reduction in live storage hectare meter per year, and what is the amount of live storage, percentage of live storage it is reduced. So like this is the main purpose what we are using, how we are using the satellite data or remote sensing technology to estimate the capacity of the reservoir. So that this is the elevation area capacity table, which is table we are. So I think so. I will be having 5 more minutes.
I think if you can, we are going behind very much behind the schedule. Could you quickly sum up?
Okay, just I will skip all these things. This is all the subpixel methodology. That this is subpixel methodology used. Just I will tell that only that when you are using the water spread area, we in the border pixels, the border pixels of the water spread area is also estimated as water spread area. So that to reduce, this gives an error. To reduce the error, we can calculate the how much of sedimentation is, how much of water is there in each and every pixel. This, when you are using the subpixel methodology, we can exactly estimate how much of water is there in each and every pixel. This is the methodology what I have used, so that we can very accurately calculate the water spread area in the border pixels, mainly in the border pixels. So it will be having problem, so that errors can be reduced. So I will just rush up. So these are all the formulas, which is this one method. One important thing is when we are using the per pixel methodology, we will be getting only one output. When we are using the subpixel methodology, we are having different outputs. This is known as, this image is known as the water fraction image, and this is the vegetation fraction image and the soil fraction image. In the water fraction image, each and every pixel will give only the water information. So this water fraction image tells about each and every pixel, amount of water present in each and every pixel. That is, say the value ranges from 0 to 1. So it is 0.5 means 50% of water is present in that pixel. So like that, only the border pixels will be having some problems. So in the border pixels, we can exactly calculate how much of amount of water is present there, so that we can reduce the errors when you are calculating the water spread area, so that the sedimentation estimated is accurately estimated without less error. So again, this is the columns. When we are using the subpixel methodology, the answer comes at 23.19 million meter cube per year. So this is when this I will show that this is the optical data. Here you can see that the white patches are the clouds. When the cloud is present in the satellite data, you cannot calculate the water spread area exactly. Hence, we are use the microwave satellite data. When you are using this optical satellite data, when the cloud is present, mostly in the monsoon periods, the steady area is covered by clouds. At that time, we cannot use the optical satellite data. Hence, for this, one more opportunities when we can use the microwave data. When you are using the microwaves, we can very clearly see the water spread or the surface details very clearly, because microwave penetrates the clouds, and clouds cannot be visible in the microwave data. So say this is one of the Hirakud reservoir. It is completely merged with the clouds. Hence, we cannot, if the satellite data is like this, we cannot use it. We have used, in this case, we have used the microwave satellite data, and this is the methodology what we have used. And again, we have you can see that the microwave data, this is the microwave satellite data, and this is the extracted water spread area. Again, the methodology is the same thing. We have to use the same methodology. We have to use select the different dates, and you have to download the data, and you have to extract the water spread area. Only the medium is different. Here we are, instead of optical satellite data, we are using the microwave satellite data, so that this is all over the year we can use. It is in the case of optical satellite data, during the monsoon period we cannot use the satellite data. Here we can use the satellite data during the monsoon period also. So this is the advantage when you are using the microwave satellite data. These are the methodologies, and again, this is this one shows that the different dates and how the water spread area is increasing and decreasing during the study period. This is again this is a chart which shows the cumulative capacity of the reservoir, and this is a short. And the conclusion of the study is that when you are using the per pixel methodology, we have used 22.6 million meter cube is the average yearly storage loss in the Hirakud reservoir. and when we are using the subpixel methodology, it comes around 23.19 million meter cube. The microwave satellite incorporates most covered peripherals of the water pixel. This leads to elevated estimation of the. Therefore, in assessment of reservoir sedimentation studies, microwave satellite substituted only for cloud covered optical images. So I have taken more images. So I will conclude with this one. Thank you, sir. Thank you very much.
Thank you, Dr. Jeyakanthan, for a very, very informative and nice presentation, right from giving the technology, the analysis, the presentation, and how to work out the water spread and deterioration in that. There were a lot of queries from various people, but we don't have time to take all those queries, including the query, how are you going to measure the sedimentation in reservoir? So I think you could reply to them through email to those respective people. There were some questions in that. We are already behind schedule by more than half an hour. So I will request, thank you very much, Dr. Jeyakanthan, for a nice presentation.
Thank you, sir. Thank you very much.
Now we invite our next speaker, Dr. Asifi from IRA, Tunisia.
Dr. Arjumadatta Sarangi will be next speaker, as Dr. CCP is unable due to some reasons. He will not be able to deliver his lecture today.
Okay. Okay, I invite Dr. Archana Sarangi, Senior Scientist, Water Technology Center, IARI, New Delhi, for a talk on application of geospatial tools in hydrology and agriculture water management. This is the most crucial area, especially if a country like India, which is dependent on agriculture. This will be a very interesting talk. I invite Dr. A. Sarangi to deliver her talk.
First of all, I would like to interrupt here, sir. I would like to thank Dr. Jeyakanthan for his wonderful lectures. I hope all the queries will be answered through the email, sir. I would like to give a brief introduction of Dr. Arjumadatta Sarangi, sir. He is Principal Scientist in Water Technology Center, ICAR, IARI KOSA Institute, New Delhi. And he has developed expertise in the research areas of hydrologic modeling in the watershed systems by using geospatial tools and models in integrated water resource management and design of the filtration unit of groundwater recharge shaft. He has received Jawaharlal Nehru Award for his significant research accomplishments in agricultural engineering, Fellow of National Academy of Agricultural Sciences, Fellow of Institution of Engineers, and Bharat Ratna Dr. C. Subramanian Award for Outstanding Teachers. He has also been awarded by the Boycast Fellowship by the Government of India and Postdoctoral Fellowship in Sustainable Agriculture by McGill University, Montreal, Canada. Welcome, sir. Dr. Sarangi, sir.
Madam, I think he is not there. We can move to the next speaker, Dr. Gerald. Augusto.
Dr. Gerald's lecture is not been scheduled for today. I think his lecture is scheduled for tomorrow, sir. Ravi, sir?
No, he will deliver lecture today.
Okay.
You can invite him, madam. He is there.
He is there.
Who is the
Dr.
next
Gerald?
speaker?
Dr. Gerald is not here, sir. Ravi sir, I think Dr. Gerald is not here. Next is the
Salni,
Dr.
Yes, sir.
Francisco.
Salni, Dr. Gerald is here.
Oh, Gerald,
Okay.
Dr. Gerald has come. Okay, welcome, Dr. Gerald. Shalini, can you
He is there.
Good morning. Yes, I'm
Yes,
here.
yes, sir.
If
Yeah,
the other
yeah.
presenter is
give the
not ready, I
credentials
can
to
present.
Gerald?
Yeah, thank you.
Good evening, Dr. Gerald.
Good evening.
Welcome to this nice workshop.
Thank you. Thank you very much. Then I will share my screen, and if you want, because I know that the time has been going pretty fast with the other presenters. So let me see if can you please let me know if my screen is being shared.
Yeah, it is shared.
Okay, excellent. Thank you very much. Then, for this presentation or in this workshop of many topics related to remote sensing and GIS, my contribution will be on a bit on hydroinformatics. And for this, I would like to just let you know a bit of how hydroinformatics is dealing with the combination of the information from remote sensing and models, hydrological models, to build up on understanding and going further in the concepts of analysis of extreme events and water resources. So for this, I want to first introduce the institution where I belong, which is the IHE Delft Institute for Water Education, which you can see here in the screen. This is the picture of the building. And we are a member of the United Nations and the water family. IHE is the only education institution within UNESCO focused on water. And we aim up on all the targets of the United Nations in terms of water and sustainable development goals. Now, this institute has been growing in the last 50 years, and in fact, the concept of hydroinformatics started here with Professor Michael Abbott in the 80s and the 90s, and with his connection with the different institutions like the Danish Hydraulic Institute, the HR Wellingford in England, and also, of course, Deltares nowadays. Delft Hydraulics in the past, and now is Deltares.
Dr. Gerald, you are not audible. Can you increase your volume a little bit?
Okay, I really don't see how to do that because let me see. This is the Jabra system. If you can see here, let me see. Yeah, I am here in the maximum. I hope it's. Can you hear me better now?
Yep.
Yep. Oh, okay. Thank you. Thank you very much. So, as I was mentioning, this is a map of UNESCO IHE alumni network. We have a Master of Science and programs in different areas of water resources, and the coverage of people that comes to study with us is quite wide around the world. We have more than 23,000 alumni around the world and 119 countries. The Institute, just to close the introduction of the Institute, strives for the training programs of universities and research institutes. We do cooperation with different institutes around the world to aim at the sustainable development goals and developing technologies for the water sector. We have 128 academic staff, 103 PhDs, and all active doing any type of works related to water. So everything is water, from the areas of governance of water till nanotechnology on water. And what I'm going to present is just one piece, small part of what we are in our institute, which is the hydroinformatics component. And mainly this is the machine learning that is being used in the component of hydroinformatics that I'm going to show. There are other areas, but I'm going to focus for this talk in terms of water resources, GIS and remote sensing, and IT technologies. Now, to have a better context of hydroinformatics research contribution and what is this hydroinformatics idea, I presented this table, which shows of how the research is being developed in different areas. So on the columns, you can see social science and environmental and earth system science. And on the rows, you can see basic science, maths, physics, chemistry, statistics. And the other row, you see computer science. Now, there is a high development in terms of social science and basic science. So we have a concept of human behavior, participation, conflict resolutions, and economy. In environmental and earth system science, we have the hydrology, hydrodynamics, geomorphic dynamics, others. And in computer science, we have mobile technologies coming up, web platforms, incorporation of social media, etc. And the last one, in terms of environmental and earth system science, we have virtual reality that has been applied to these systems, forecasting systems, and advanced modeling. So where do we work? We try to link all these problems and all these science aiming at water scarcity, so understanding drought consequence, resilience to it, floods, again, what is generating our floods, how much they are, what is the impact, how can we manage the risk of floods, the food production risks, if we have water scarcity, then what we'll do to produce our food, and water in energy production in the world. So all these components are, in fact, related to human intervention, society, and the stakeholders. Aside of this, there's environmental variables, of course, which I didn't highlight in one box. But what you can see is that most of these topics relate to this conference. This international conference in water, energy, environment, and society. Now, this hydroinformatics, how all these technologies integrate and how can we use them in improve water sustainability can be shown in one of his areas by looking at the phenomena like rainfall runoff. And what you are seeing here is, in fact, part of an analysis that was done for climate change in Dominican Republic in Central America. And this is just an example of how the variables change and how to understand this phenomena. In this case, if you are talking about climate change, the first thing that people look is at temperature, and you can see how the temperature have a cycle and frequencies that are periodic. So it's kind of a variable that, although seems to be pretty clear to understand, it has many peaks, and trends and outliers of it are very difficult to understand, to find the anomalies in the temperature. Well, you can see that you cannot say something concurrent about this phenomena. If we look at the precipitation, well, it's even more difficult. And this is where rainfall runoff processes begin. And if you look at this graph of more than 20 years of rainfall in that region, well, it's the phenomena shows a couple of peaks and tell us about the frequency of these high events, what are this intensity of these high events. But aside of that, we do not understand how these events happen, what was the characteristics of the event, how it covered the region. We just know that was a peak, very high value of average rainfall. So how to deal with understanding more of this? Via analyzing and linking the information for remote sensing products. Like in this case, what you are seeing here is a river basin in Brazil, where we applied a continuous drought area adaptation method, which is in fact a pattern recognition that integrates in 3 dimensions the information from the rain. Therefore, we can see extreme events, not only in one dimension, not only in two, but this is in 4 dimensions, where the color of each one of the cells that you are seeing that is falling into the river basin shows the intensity of the event. So this will help us, these methodologies are helping to understand more how these extreme events are represented, like figures in 3 dimensions, like this one that you are seeing is the same event with the scales adapted, but you can see more or less how the event happened, what are the morphology characteristics of the event in time and in space. So we are trying to link these 3 phenomena to be able to increment the information that we have for different types of modeling systems. This is another one. This is an analysis of drought areas in Mexico. The methodology was developed such that we can integrate indicators of drought per space and time. So what you are seeing on the left graph is the SPI, this is a Standardized Precipitation Index, and SPEI, a Standardized Precipitation and Evaporation Index, with a scale of 6 months integration. And the colors are showing the areas where we could find cells that had values below a threshold. And the spatial integration on the left side shows the time series of how the area that goes below a threshold is changing, such that you can see that the event is not only the event in 1 pixel or the event in certain area, but is how the aggregate of the different levels are changing in areas around the basin. With this, we can see if there's an extreme event is not only in one small region of the whole basin, but how it is being distributed. Maybe it's only in the high part, only in the low part, or in the middle. And this type of droughts might be happening in different ways along the year. So some droughts that have some intensity can be identified in certain periods. Going a larger scale, this is a representation of the same SPI, but in Colombia, and how the regions synchronize the events. And this is very, very important for agriculture, for example, where you can see if 2 regions which are producing the same type of crop might be compensating in the way that one probably is in drought, but the other one is not. Or if you have a synchronicity in between the 2 droughts in 2 different regions, then you have to take actions, because you will not have any more that crop, or you will have a very low production of that crop due to the low availability of water. Now, this on the right side, what we were testing is the same analysis and seeing how from the left, that is the meteorological drought, to the right side, that is agricultural drought, where we incorporate the SEDI indicator, which takes into account the actual evapotranspiration, which tell us a bit more how much the water was on the soil, how the soil was behaving, and how much this is different from the drought indicator in the standard precipitation index. Now, what I'm going to show you in the following slides moves into artificial intelligence and machine learning. And I'm going to show some slides of a course that we just gave this year in Brazil with the University of Campinas. And now we are going to produce probably online for the next year, so 2021. And the main concepts behind this goes into bringing the basics of artificial intelligence and telling how the evolution goes from the concept that born in around 1950s in Cambridge, and the first conferences where they started to talk about artificial intelligence, and its evolution through machine learning concept, which I think many of you have used already in remote sensing or are thinking about the remote sensing, and the recent, relatively recent, so 2010, the boom in using this deep learning. And now, how can we use this deep learning, or how it's being used in different type of spatiotemporal analysis? To do that, first, I think it's important to understand the concept of these machine learning models. And I am taking one of the slides of the lecture of Professor Dimitri Solomatin from UNESCO IHE. And this is a slide that is meant to explain how the machine learning takes blindly, let's say, input data and output data, so actual observed data as the output of your system, and the measurements of the input to reproduce the reality. So this is a machine that is learning from this output and this input. And what it tries, the machine learning, when you build the machine learning, you need to change the parameters of the model such that the input and output are minimized. And that minimization is called the learning process of the machine learning model. Going in a bit more technical explanations, the concept of machine learning normally is explained by first going in a scale of complexity. So here I put these 4 colors on, more or less trying to explain the complexity and how it grows and how it brings more and more information. So the concept of one neuron can be similar to understanding a linear model, where the output of the linear model can be analyzed as if it goes above certain value is a class A, or below certain value class B, which will be a kind of classification problem, and your model is just a simple regression. Or could be a simple regression passed through what is a decision algorithm. Or 2 can be used as a simple core of computation, where you can see we can add as many input as we wish, the same concept of the linear models, with a number of weights. And then we have an activation function A, like this one, which is the sum of all. Again, is a linear equation. And then that algorithm that I was telling you, which is that if there is a threshold where if your function is above the threshold, then your output belongs to certain value 1, or its a value is 0. What's the meaning behind this? For example, if you want to understand a flood situation, you have a lot of inputs and you have some outputs. That what happened when you have these conditions, the output was flood or no flood. So your 1 will be flood situation, your 0 will be no flood situation, and the parameters that you need to find are the W, such that when you input those X, you will have this output of this linear equation that will go above the threshold, and then you have fitted that the situations where you have a flood, and if it's below, then you have the situation that fitted no flood. So flood and no floods based on your change of weight, and that's what called the training process. Now, in a one neuron, it's something as simple as like this. But if you have various nodes, so you combine multiple linear equations, so this is 1, 2, 3, and then you have multiple layers. So I have one line here that shows the first layer, which is input, second and third layers. And then you see also these units of linear regressors are being integrated. And there are multiple structures of networks developed around the world. In the last 10 years, there would be thousands of different concepts that tells you how to combine these linear networks such that you can improve the way that you can mimic almost everything in the world. It tries to mimic everything. Everything that you have measured, inputs and outputs, you should be able to have some sort of network that will help you to do it. Of course, this is not magic, and the challenge here is the mathematics behind trying to learn those weights and this complex combination of linear and non-linear functions. This had ended into variations. So what I showed, this is various neurons, but then it enters into variations of networks. And then if you go to the literature in remote sensing and in areas of related to machine learning in general, you will find multi-layer perceptron, which is the one that I just showed, multiple layers, and perceptrons are these nodes that I was explaining with linears. You can have self-organizing maps. You can have support vector machines. You have deep networks, which multiple layers of that I was showing. So that's making the network deeper and deeper and deeper in nodes, which makes the computation highly intensive and requiring high computational machines. And therefore, not everyone in the past managed to work with these deep networks. And that's why machine learning had a jump where you will see deep learning, how to learn from this deep type of networks. One of the ways to learn in these deep learning systems is to use what they call convolutions. And for example, this is convolutional neural networks have been integrated with deep learning networks. And the convolution neural networks are networks that simply try to have your matrix of your remote sensing images. I'm just giving an example. Of course, this is done with normal image recognition. Most of the literature of Google and Facebook and so on is with image recognition. But right now, I would like you to think into a remote sensing product, which in fact is just a simple matrix. And in that matrix, you could take a pattern, something that you want to recognize, and then you will try to filter that pattern. So you move this pattern along all the cells around your image. And that is the convolutional process, where you are reducing a big, large image with thousands of cells and passing some sort of filters that will be layer by layer. Each filter is trying to identify or highlight certain characteristics. By having multiple of them, you will identify properties one by one, and at the end, you will have a convolution, a normal multi-layer perceptron that will integrate the results of those filters into a neural network system. Recurrent neural networks is the last one that I want to show. Is also one of the latest approach in deep learning. Also, this is a long short-term memory, and it's also a kind of combination of multiple nodes. And the way this algorithm broke the conventional concept is that there used to be an idea of having a time series continuity, where the recurrent neural network normally only take it the previous one or the previous and the previous, like an autoregressive model. And in this case, is taking not only the previous and the current one, but also taking into account a memory one inside the network. So this of course it will require a full lecture to go into detail on how to explain this, the concept of the network, but more or less with this, I hope you can understand that there is a variation in the concept slowly evolving in the history of the development of machine learnings. So machine learning, what you can find have evolved, and it maps also into how in water resources have been done. Like, for example, sound, where right now I'm talking, if someone makes a frequency diagram of the waves of my voice, this kind of technology can be also mapped into what we use normally in a runoff time series. Like you can see here, making a model of the voice can be the same as making a model of the time series of a runoff phenomena. Another one is, as we were talking a few minutes ago, image recognition, trying to identify patterns like these faces. This is highly advanced. As you can see nowadays, even in China, you have some places where you can pay directly only showing your face, and they recognize the face, and then the bank makes the transaction to pay the restaurant or any other activity that you were doing. And in our case, what we were seeing a few minutes ago with some of the presenters is to implement systems that can recognize, for example, pixels that are trained with surveys where it can help you to identify different characteristics, or even identify non-direct properties through unsupervised learning concepts, where we can identify situations with like flood, no flood, and so on. Another example is this, for example, in science, we know in physics the Large Hadron Collider experiment, big data, how this information is used is very complex. But now in climate change, we are also having this large amount of data. You can download right now, tomorrow, anyone that wants to just go to the CMIP project, the multi-model intercomparison project of climate models, and I would say the most well-recognized institutions in the world have developed models for the whole Earth at different resolutions for the last 50 years and for the following 100 years. Yeah, timestamp of even hours. And you can imagine the amount of data that represents for us to try to understand how these models are telling us information on the water and the hydrology. And last one is one of my recent PhD students is really interested, and was won an international competition on how the people use water resources and machine learning, is the idea of using natural processing language, digital media. And this digital media is like right now a website, an organization, for example, in India, could be producing reports and reports and reports about water problems and so on. And we can have even on the other side news about how the people have the perception of a river system or a reservoir or the agriculture or the water needs or the water quality. But all that data is there right now on the web. How can we use it? So at the end of this presentation, I will show you a very interesting example how natural processing language can extract information, and we can map it with the way that we are taking decisions. We can make intelligent decisions and learn from what it's there already in terms of data. So now, what is AI in water resources? It's in the simulation of events. You will find many papers right now in these 4 areas that I'm showing you. The simulation of events from forecasting rain or discharge to using this into early warning systems and to have surrogate models that reproduce phenomena. We have image classification in remote sensing, land use change, flood classifications. We saw some examples again in the presentations before mine. Decision making, and this is what I mentioned before, how the news or digital media is used in natural processing language. And last one is the concept of spatiotemporal model agents, cellular automaton pattern tracking. How can we identify how these remote sensing images or the data that you have from models are telling us the phenomena are moving around our regions, our basins, our continents, and so on. Okay, to close this presentation, I want to show 3 examples of ideas. The first example is forecasting, flow forecasting. This is a rainfall runoff model, and it's being reproduced by lag precipitation, lag discharge as input. And the characteristics of these models are that have fixed time step, they're highly accurate, but there is no clear knowledge representation. So they work like this, like for example, an artificial neural model is trying to learn what will happen with series of input in a forecast horizon. Another example is the optimal reservoir operation, and this is a very interesting case which will be presented at the international conference in Latin America about reservoir operation. And the idea is to have an intelligent reservoir operation, not anymore based on certain rules that has to be adapted depending on the situation. But this intelligent reservoir operations uses equations to minimize the floods, maximize the use of the water for irrigation, and maximize the energy production. What we did here was to first make a model that learns from the previous years. So was first learning how the people were doing, And then after you learn how to have a model that knows how to deal with the operation of the reservoir, then we put an optimizer that took this what it had learned and improve it such that it have 3 dimensions, a multi-objective optimization of the reduction of the floods. And what you can see in the graph of this time series is the how much we could reduce. You could reduce almost 80% of the inundation if we had this type of intelligent operation into the system. These are some of the results of the operational system. The third example is about droughts, and I mentioned a bit about it at the beginning of this presentation and how the droughts can be identified in space and time. But to go deeper or to show you just an example of how this can be used with machine learning is this region in India, Eastern India. Of course, you are all aware of it, Bihar, Jharkhand, West Bengal, Odisha, and Assam. And excuse me for my pronunciation if it's not the accurate one. But there is a large production of rice. 35% of the total area is the rice, the dominant crop there. And what we wanted to see is how much the effects of these drought indicators can be used to, let's say, have a forecast of the crop yield. So by understanding the percentage of drought areas that can be obtained from remote sensing image, we could have a good correlation with the crop yield, and especially with the anomalies and the intensity of the impact of the drought in the crop production year by year. So this was quite interesting result, was very good forecast. A second one was the idea of trying to find in the whole India. This is a representation of the largest droughts that happened in the last 20 years of data from rainfall information from these global models. And what we get here is just to show a theory on how we can represent these spatial regions that I was showing in the previous graph and make clusters, and how these clusters start to change and move all around the country. And with that, we make a tracking analysis of the centroids that will allow us to say that there are patterns on the way that the droughts are being generated in India, such that in the future, this information can be used by the people in the country to take actions on the different impacts in their crops. Oh, and I forgot the last one, which was the idea of natural processing language and going into areas of IT technologies, is this analysis of what is a sustainable river basin and how the information from digital media can be used. So this is a very simple representation of one large river basin that is called Magdalena in Colombia, and it has, of course, hydropower generation. It has irrigation systems. It has its environmental law and environmental policies. We need to protect the environment, of course, and of course the human, the society, and the water needed for the society. So these are the typical conflicting elements, and we have targets year by year. You can see on the right side of this screen indicators of floods, indicators of agriculture production, indicators of hydropower, river health, forest, and so on. And there is a kind of monitoring through models of what each one of them is doing, how these indicators are changing according to the different policies that the country is taking. So how this is working, how the decisions are made is the key question here. How do you decide to produce or more or less energy, or to protect the environment, or to produce less to provide enough water for your food production, or vice versa, to have enough water for the city, and so on. So these decisions are sometimes, or most of the time, conflicting. And the idea of a decision, you have here on the lower part an analysis that says the problem, comes, the government has a proposed solution, there is a decision making, and there are consequences of the decisions. And the upper part, you have digital citizen media information, which are the newspapers, are all the different organizations and online reports and so on. And there is an interaction where how the people read this media and how the people informed influence this digital media. So there is a kind of cycle between two. But aside of that, so the citizens, or these links between the citizens and the media, influence the way the solution is proposed, the way the decision is taken, the way that the consequences are interpreted, and so on. And this is an experiment on analyzing how a river basin can be understood and how the decisions were taken based on different priorities. This is the last two slides. And what we are seeing here is the result of extracting more than 22 online sources in the country, extracting information of each one of the river streams of the Magdalena. Here is the map of the country, and year by year how the newses were changing and how the information, we are extracting that data on converting it into an index that will tell me how the people were feeling about, or how the text of the reports and the information, extracting key elements of the syntactics and the grammatic and the syntactical, the meaning of the way that the text is reading, it's going into a negative, neutral, positive, or no information concept. Via doing this, we can analyze how the system is changing when a decision like the construction of a reservoir between one year and the other, the alteration of a system in terms of environment, fishery, and so on. The left side shows two of our examples where we managed to identify the levels of feelings for the constructions of different hydropower, and one was water quality in the Lake Funike in the Cundinamarca. All this was produced and implemented into Google Earth Engine with the information from Google Earth Engine and remote sensing products. And that's it. I think what I wanted to leave you here with a couple of ideas of research and areas that are very interesting in terms of hydroinformatics. And with this, I wanted to leave you with questions: how to become more sustainable with all this information, how to be more resilient, and how to improve our links between remote sensing information and spatiotemporal phenomena. And that's, thank you for this time for this presentation.
Thank you, Dr. Gerald, for such a nice presentation on how artificial intelligence and ICT, modern technologies, can help in hydrology and forecasting, even forecasting of drought and forecasting of information on hydrology. It was an excellent presentation. Thank you very much.
Thank you.
Do we have time to take a couple of questions, Shalini?
I see mute, Charlie. Sorry.
Shalini, can we have a couple of
Yes,
questions for Dr. Gerald?
Yes, sir. There are two questions. We can brief them shortly. Dr. Gerald, one of the participants have inquired that how AI and MI can be implemented in the examples, how the AI and MI have been implemented in the examples discussed. Are there any specific software which are used to be implemented in the various algorithms? Can you name some resources?
Yes, yes. We have been using Python libraries, sklearn, and the TensorFlow modules that allow us to integrate different type of algorithms. That was one of the things that we have used. However, we have created also our own libraries, and we have been doing different different tests. Deep learning, we have been using also MATLAB libraries, which are also quite efficient. We have been using also some specific software, especially for training, and some of the simple cases of forecasting to get the concept. We use Weka library from Australia. So there are different tools made for each one of the problems. And I would say the basis for the people that want to start, first try to look at the simple examples with one of these learning tools, which is not so powerful like Weka, and then go into starting to learn these technologies like TensorFlow and going even higher and higher.
The second question is how to apply AI for food security in Africa.
Okay, AI and food security. Well, there are many. This is yeah, I would believe it's an open question. There are many areas that right now AI is being used. Like one of the examples that we were seeing is trying to learn about the past and the consequence of droughts and how this affected the crops production. There are others, in fact, related to the different type of social relations in terms of sustainable development equations for sustainable development goals, and how the hydrology can help us to understand the energy production and other variables that link to food production as well. So this is, I would believe there are hundreds of possibilities.
Thank you, Dr. Gerald, for enlightening the use of artificial intelligence, machine learning, and deep learning. We have focused how to use these tools in the area of remote sensing. And I'm sure that the tools which are used in the different streams are now have become multidisciplinary and can be used in all the areas.
Yep, indeed.
Thank you so much.
Thank you for the invitation.
Now, our next speaker is Dr. Francisco Munoz Arriola, Associate Professor, BSED, University of Nebraska, Lincoln, from United States. Welcome, Dr. Francisco Munoz Arriola, for your presentation on climate resilient water infrastructure and complex agriculture landscape, integration of data management and policy. Welcome, Dr. Francisco.
Thank you very much, and thanks to the organizers for your kind invitation. And well, first of all, can everybody hear me and see the presentation?
Yes, sir. We are able to hear you and see the presentation also.
Fantastic. Thank you very much. And I'm going to take advantage of some of the ideas that Gerald brought and some of the colleagues previously today and yesterday to show basically some of the examples related with these topics that I'm going to mention today. Well, I would like to start with the motivation slide, talking about the acceleration of the human enterprise. Extracted from Stephen in 2011, we observe how our human enterprise have reached levels, unprecedented levels of growth in many areas. We can think about the negative side of things as well as the positive side of things in terms of how we provide resources to sustain a growing population, to reduce the release of CO2, reduce our vulnerability to floods, improve our vulnerabilities to losing biodiversity, storing resources, increasing the wealth, as well as using less resources, and mitigate the problems of pollution in our environment. These are some of the wicked problems that we face, and that we are going to try to integrate different resources in order to track, to model, and to provide solutions to them. in particular in the realm of remote sensing data, a little bit of artificial intelligence in agricultural landscapes, or what we can call water for food production and productivity. The outline, as I listed here, will go through definitions to the identification of a socio-environmental system. I will pose a thesis and a couple of premises that will be followed by a methodology that will be aimed to list the abilities to forecast resilience and to basically illustrate other complexities in our system. And I will finalize with the concluding remarks. Among the definitions, I have the simplest one that we have already, or everybody in the room knows because of the expertise or because of the interest. But the key aspects that I would like to have that are highlighted are three: regarding the definition of remote sensing and the definition of resilience. And I'm gonna focus on those highlights: information of data or data. I will focus also on systems or systemic perception and the systemic evaluation of the environment and our interaction with the environment, and how we disturb that environment and how we manage the environment in order to preserve basically the state, or what we consider in our current socio-environmental state, without transforming our system into another more stable state. Obviously, what we are looking at here is into the letter B and the ecological resilience, which is basically try to identify those functionalities in the system that allow those systems or infrastructure to basically be maintained in a stable state without being transformed. Although, if we think about the transformation, we can also think that there might be transformations that are positive as well. And let's see if we can identify some of those in the following slides. So our socio-environmental system, as the first part of the talk, is basically the Ogallala, the Platte River, the Ogallala Aquifer and Platte River socio-environmental system. It's illustrated here, is in the heart of the United States in the Midwest, and is located specifically in the intersection, is located in the Northern High Plains in the state of Nebraska, where I reside. And what we observe are the different states that are involved or share this common pool of resources, which is another concept that we are gonna tackle, and we are gonna try to integrate this, the social component of the environmental system that we have in place. In this pursuance of evaluation and the preservation and recovery of systems, we see in our path toward basically satisfying the increasing demands of food, water, energy, as well as ecosystem services, just to mention 4 of the key pieces of infrastructure that drive the human enterprise and the relationship that it holds with the natural environment. The sustainability of agriculture is also related with the sustainability, with the increasing or the intensification, as I mentioned here, of data. On the left-hand side, we observe the yields in 3 states in the Northern High Plains, or what are called the Corn Belt in the US. Basically, 1/5 of their production of agricultural produce occurs there and represents about 6% of the GDP of the country. And what I want to evidence here is the increasing production of a combined soybean and corn in these different states. What you observe in the different colors for Illinois is in light blue, for Iowa is in black, for Nebraska we have 2 different time series which are in red. The one at the top is the one that is based on irrigated agriculture. The rest, including the one at the bottom for Nebraska, are rain-fed agriculture. What we also observe in this particular case is basically the role that technological development have played in improving agricultural productivity due to the genetics, due to a better understanding of the complexities of the soil, as well as some introduction of the technologies such as irrigation, which just bump up the production of these grains in the northern high plains. But what we observe as well, and is the focus on the following slides, later on where I will be talking about the drought, but what we observe in the case of the flood, in the case of the drawbacks, and these positive trends is when we have the occurrence of extreme events and the ability of our systems basically to interact and to recover or to recover those functionalities that enable them to continue producing toward this positive trend. But as we observe here, we have the effect of the flood of 1993 with 20 billion losses, or the effect of 13 billion losses in the case of the drought. And what we observe on the right is an article published by Overpeck et al. In Science in 2011 that shows precisely something that's close to our heart today, and is the satellite radar availability of data and how it is increasing over time, together with those emerged from modeling resources and those that are typically stable, which are the in situ and other kind of sources of data, which I have a little bit of discrepancy with that, because with emerging of proximal sensing technologies, we also have a lot of resources available. I don't know why I have these blue lines at the bottom. Forgive me, I don't think I have moved anything here, but we'll see. Oh, thank you. And so in the case of the flooding events as the effect or how they impact the sustainability of agriculture, we faced just last year, at the beginning of 2019, a tremendous impact of a flood event. And the interesting aspect of that flood event, besides what we have at the very end, is that it was basically the product of compound events. What that means is that we have a series of events that not all of them were extreme by themselves. And this brings a couple of challenges to decision makers, to policy makers, and to people that works in the area of a policy design as well as infrastructure design. So we use different resources. What we observe in this compound event to illustrate what are the challenges is that we have a tremendous impact of or accumulation of snow. That was at the beginning of the year, talking about February. That was followed, and this is the hydroclimatic aspects of this, was followed by a typical or even below average precipitation event, but was a interestingly high temperature or enormously high temperature, which basically melt down all the snow and ice that were accumulated, causing the problems of flooding in the lower lands of the northern edge or tributary of the Missouri River basin. These are basically some of the attributions and expressions in terms of the anomalies, the temperatures, and the snow melt. What is clear is that not either as a compound event or as an event that was not typically strong, it was not considered or is not part of the standards or the policies related with decision making. So that is one of the reasons why the flood storage or different storage capabilities were jeopardized by this kind of event. And here is one of the syntheses and how basically this particular event end up affecting the crops is again, it is occur at the beginning of the year. The growing season is between May and October. So we even have effects on that growing season because of this event occurring early in the spring. And using Sentinel-2 data with 10-meter bands and 5-day images, we captured basically and selected the areas that were both damaged and contain a particular layer or a defined layer of water that disabled their ability to produce. And this was captured in the time series of, or the difference in time series between growing seasons in 2018 and growing seasons in 2019. So that delay in planting, that delay in the growing, and that eventually a potential delay, or not necessarily a delay in the harvesting, affects the breeding abilities, affects the type of seed or the type of crop that should be grown, or the type of variety or hybrid that should be selected. And that's something that has to be included somehow. Now, what do we have in the next slide is basically conceptualization of how this event affect a series of infrastructures and what are the different aspects related with the predictability, with the existence of standards, what we consider the potential resilience, and how an event that initially starts as a water in excess turns out to be an event that is equivalent to a deficit in water. And the main reason I mentioned this deficit in water is because of the poor quality of the water in the aftermath of the extreme event, no matter that the quantity is in excess or remains in excess in the area. The other aspect is drought, and the sustained agricultural intensification is also brought down when we have events such as the 2012 flash flood in the northern high plains. Data such as the modest leaf area index that later on is used to force a land surface hydrologic model, such as the variable infiltration capacity model, are useful resources to identify the water availability and the impacts on land use, or how land use interacts with hydrological properties in order to define the availability of water in different regions at the largest scale in this particular case. But we can also think about how this availability of water, or the lack of available water, basically affects the agriculture and affects the urban entities at the same time. And in areas where we have a strong surface groundwater interactions, or where we have the availability of groundwater, is particularly important, because groundwater becomes a subsidy for the deficit of water, becomes a social subsidy, becomes an economic subsidy, and becomes a geophysical subsidy of that lack or deficit of water availability. And we also intersect here in what kind of data we have available. We have in this particular case to track or to identify, and this is an effort work together with the IHE, and Gerald is part of this effort, and a PhD student who is currently in the Politecnico de Milano, Alessandro Amaranto, and others who have contributed to identify the potential of using groundwater well level lectures in our records in order to predict and train a neural network and identify subseasonally what would be the changes in groundwater well level, and eventually the ability of the system to overcome or recover functionalities. That means that we can produce food, or we can sustain the different ecosystems. So this is the intersection of how we manage water resources, is when we introduce the social component here. And in Nebraska in particular, the administration of water resources is considered one of the most progressive forms of management or managing water resources in the US. And the reason is basically the administration of water occurs conjunctively between the surface water and the groundwater, where the Department of Natural Resources District has the task to manage the surface water, bring together 23 different natural resources districts that basically manage the subsurface, the water in the subsurface that is basically used to irrigate some of the cropping lands in the state. About 63% of the territory of the state, it's considered areas for considered areas subject or potential growth, agricultural potential areas of growing produce. And this is the management, the policy aspect, how we can basically regulate and at the same time preserve the ecosystem services and produce or make sure that one of the main drivers of the economy of the state is preserved and it contains. So among the data that we have available, and as I observe here and moving to the next section, is in the map we observe the state of Nebraska with about or with more than 95,000 registered wells, which is a wealth of data. Problems with the data is that this continues in terms of their time series or are heterogeneous in terms of the spatial distribution. We don't have all the data and all the times and all this data. So the thesis is that the integrated remote sensing in situ and modeling-based products by learning or machine learning techniques in this particular case predict the aquifer resilience to policy implementation and to climate or weather events, in particular, the deficit of precipitation means drought. The first promise emerged from the paper published by Alessandro Amaranto in 2018 in Journal of Hydroinformatics. Contributions of the multidimensional hydroclimate and management related inputs, that means the data that we have predict the groundwater well level changes using artificial neural networks. Premise 2, and comes from a paper that we recently submitted, the collective action dilemma is captured, which is basically related with the common pool of resources and how we misuse or use it, affecting the rest of the members of the community, is captured by the estimations of groundwater well level changes based on remote sensing and in situ data. These two premises then lead us to establish this methodological framework where we integrate our socio-environmental system, the Ogallala Platte River Basin, mainly working in the low proportion of the High Plains aquifer, the Ogallala aquifer, or the Northern High Plains in terms of the regional context. The framework is the modeling of the collection of hydroclimate data, the selection of the input variables, the training of the models, and the evaluation and the comparison of these different models. 5 different machine learning techniques were applied. The next step is how we can identify the different states of change and evaluate the results as a function of or driven by the climate and land use. Both have in common the assimilation of remote sensing and in situ data and the integration, obviously, of both of them to basically land these actions into what is the policy and management context based on the reaction of the groundwater system to these policy changes and the inter-NRD or natural resources districts comparison. So we're going to look into 3 different natural resources districts that are hydrologically driven, and we're going to compare the changes in groundwater well levels, and we'll all embedded in the data. We'll see if the implementation of policies will be evidence and can be simulated in prognostic within a prognostic window. The combinations that leads to the use of the variable selection model that will enable us to reduce redundancies and to have an improvement in the computational time and obviously an improvement in the forecasting. I will not go into deep in details of what are the different components. You can see some of this information in the papers published by Amaranto. The next step is basically the integration of these different hydroclimate inputs, which are precipitation, evapotranspiration, or crop evapotranspiration. We have the groundwater well level changes, and the main purpose was to basically define lead times in between 1 to 5 months. The other aspect of the is the evaluation of the performance of the different models using basic efficiency techniques, such as the root mean square error and the Nash-Sutcliffe efficiency index, as well as the receiver operating curve. So let me bring the other component of the methodology, which is the more abstract one in terms of the collective action dilemma. That means the tendency of the individual users to exploit the natural resources and contribute to the tragedy of commons. That means how a single person might affect the common resource, in this particular case, the aquifer, the Ogallala aquifer, the overdrafting of the aquifer, just because a group of people started to extract more than the water that is available to everybody. This is consistent with the crop depression, and it responds to basically some interannual and interseasonal changes. As you could observe in the plot at the bottom, we see the groundwater depth changing with respect to time. And what we observe is this depletion of the aquifer, basically in response to the use of groundwater to satisfy the evapotranspirative needs of the crops, and those crops that are growing and that are increasing in terms of the area growth, the growing areas. But in 2005, 2006, there was the implementation of policies that basically reduce the use of the withdrawal of water from the stream flows. In areas where we have a strong surface water, groundwater interactions, the recovery of the stream flow lead to the recharge of the aquifer and then the increase in the level. That recovery is a product, what we consider a product of changes in policies. However, the drought of 2012 exemplified in this area is also impacting those groundwater withdrawals, but also the reducing the stage in the streams, so causing a depletion in the recharge of the aquifer and affecting making the policies or reduce the effects of the policies. So we have different cases, as I mentioned, 3 different natural resources districts where we have no policy recovery, we have depletion, places that didn't implement. We don't mention geospatially, neither explicitly what were these natural resources districts, just for security and because there was no disclosure or the NRDs didn't want to disclose this particular information. So the third part of the talk is toward the end and how the artificial network performed. Alessandro Amaranto published this, as I mentioned, in 2018 in Journal of Hydroinformatics. We observed that basically different models and different lead times, the performance of the neural network was fantastic. As we can observe here, the differences in the ROC, which we could see the perfect match between observations and the simulations would be tracking basically or following the boundaries of the plot. And we observe that, yeah, the response when it's above this line is about 50% equivalent to a Nash-Sutcliffe index, or approximately that, will lead us to have a good performance, which vary between 0.7 and 0.90 in the Nash-Sutcliffe efficiency index. We see the wells especially distributed, and in 2019 and 20, Alessandro also produced the following follow-up papers which especially distributed the performance of the model and the relationship they hold with the inputs. And in 2020, in Journal of Hydrology, we published basically what were the main drivers of uncertainty in the estimations or the changes in groundwater well levels. This is the background information that lead us to think where are the areas that we can use to improve our ability to predict the resilience of the energies or the implementation of policies, as well as the effect of the droughts and the on the changes in groundwater depths. And it's important here is that this information can help decision makers basically when we are talking about 1 to 12-month lead times. This is a semi-seasonal time window for prediction, which is tremendously important to see what is the water resources availability, how the resources can be distributed in a place where water rights are not driven by seniority, but are driven basically are driven by the water pool available on a particular year. I would like to mention this because we have the effect of these extreme events, and I'm leading to the final slide, so I'm running out of time. But I would like to think about the effect of the extreme events is typically negative in these two cases that I mentioned. The one that is on flood and the one that is on drought. There is no positive thing other than probably something that pushes us intellectually to overcome these challenges and create new techniques and technologies. But the COVID-19 brings us new lights into how we deal with such environmental systems. And this is basically the conclusive remarks of my talk. We are about to finish a book, and I, in case you are interested, will be available at the beginning of next year. We lead by A.L. Ramanathan and other five researchers. We brought the different, or we integrate the collective thoughts of how COVID and the lockdowns associated with COVID have affected the environment. And as we could see, as a socio-environmental system, we have positive and negative effects. As we observe here, the quality of air improved in many places around India, but in other cases, the deterioration of our health educational systems were evident, not just in India, but around the world. So some of these elements bring two sides of a single coin that identify how our system needs to be recovered, or how our system, either if it's on the side of the socio-environmental system and the loss of functionality of the human-driven aspects of the system, going from planning, absorbing the change, recovering, adapt, etc., or the loss of functionality that is reduced and enable, for example, the visit of communities or the expansion of ecosystems as we have not seen for a while. Anyway, this is basically built on a resilience matrix, a very qualitative approach that leads to think how strong the physical, informative, cognitive, and societal components contribute to the resilience, to the reduction of risk and the vulnerabilities. This is a complex system. We live in a complex system with strong ties between the human and the natural environment. The conclusive remarks in terms of the numbers we probably seen, observed by the Nash subclips and the abilities of the system to reproduce, we were able to identify and integrate in the data the common source of the tragedy of commons and the pool of common resources. And we also were able to introduce other signals in the hydroclimatic and socioeconomic context to produce good results and predictive analytics. So without anything else, I would like to thank all the contributors here and And thanks everybody for listening. In case we have some time for questions, or if I am able to answer them by email, please feel free to ask. Thank you very much.
Thank you very much, Dr. Francisco, for a wonderful presentation. In the pandemic period, how the negative impact has improved the environmental aspect also was brought up by you, and how the model framework, model and the management and policy together make a complex system to bring some improvement. A very nice presentation. Thank you very much, Dr. Francisco.
Thank you all. Thank you, Jain.
Thank you, sir.
Do we have time to take, because now Shalini, only one speaker is left. So
yes,
we can take a couple of questions if there are.
Most of the participants have expressed their thanks for the wonderful presentation and have asked for the PPT slides. And I would like to give a brief introduction of Dr. Francisco Munoz Arriola, which was not been given previously. I apologize for that.
No problem at all.
He is faculty fellow of the Robert D. Dotterley Water for Food Global Institute, faculty fellow of the University of Nebraska Public Policy Center, faculty fellow of the Nebraska Government and Technology Center. He is also working as an associate professor in the hydroinformatics and predictive analysis in the Department of Biological Systems Engineering, College of Engineering, University of Nebraska Lincoln, USA. Thank you, sir. It was a very good presentation. Thanks for highlighting the latest research. I hope all the participants, all the research scholars would be benefited by your work carried out. Thank you once again.
Thank you. Thank you very much.
Now we have the last speaker, Dr. Sharad Kumar Jain, former Director, National Institute of Hydrology, Roorkee. I welcome Dr. Jain for the last talk on today's session. Dr. Shalini will provide the biodata.
A brief introduction. Introduction is a very small word to describe all these speakers, but yet definitely there are few terms which can be used for them, which will grace the occasion. As you mentioned, Professor Jeyakanthan sir, that he was ex-director, National Institute of Hydrology, Roorkee. Besides that, he has also done his postdoctoral fellow in Japan and a visiting professor in Louisiana State University, USA, and NEPCO chair professor at IIT Roorkee. He is also a member of various international board of advisors, books, journals of hydrologic engineering, editorial board of hydrological processes journal, and editorial board of journal of Indian Society for Hydraulics. He is also a chair of many expert appraisal committees for the different ministries. I welcome you, sir, for your valuable research work, to present your valuable research work.
Thank you. Am I audible?
Yes, sir, you are audible.
Yes, sir. Yes, sir. You are audible.
And you can see my screen also, I hope?
Yes, sir. Yes, sir.
Okay. Well, namaskar. I think today namaskar is the more appropriate word, which is free from time domain. So my namaskar to everyone. And let me thank the organizers for giving me this opportunity to talk to a wider audience. I will talk on assessment of evapotranspiration by satellite based data. So, Mr. Chairman and delegates, this is a small talk, and it is actually based on the work which has been carried out by my colleagues when I was in NIH. And at that time, we decided to set up an experimental basin at a place called Jijili. It is located on a tributary of Ganga called Hinwell. And in this picture, you can see a small tributary, a small river flowing here. This river subsequently joins the main Ganga river. This place is very close to Roorkee, so that was another reason why we chose to establish our station here. It is about 3.5 hours drive from Roorkee. So we were looking for a suitable place where logistics are easy, where we can go at short notice, do the work, and maybe come back to our office within same day preferably. Now, the topic that I have chosen today is assessment and validation of evapotranspiration. And the reasons why I have chosen this topic will be explained in subsequent slides. Okay. So this here you can all know that evapotranspiration is one of the important processes of hydrologic cycle. And in fact, this is of interest to a range of stakeholders working in the field of water, which includes researchers, planners, managers, practitioners, and so on. As we all know, evapotranspiration consists of two terms, evaporation plus transpiration. Although it is a very important topic in hydrology, but the importance of ET in terms of its magnitude depends on time scale and the type of hydrologic event that we are talking. For example, if there is a storm, rainstorm of very short duration, then during that time ETs are typically very small, and due to this reason we often neglect them in computations. But we also know that most of the evapotranspiration from a catchment takes place between runoff events. For example, these days, today we are in the beginning of December month. Typically, we don't have much rainfall in the catchments. So this is the time that bulk of evapotranspiration will be taking place and transporting water away from the catchments towards the sky. Now, in terms of magnitude, it can be at times about 2/3 of annual precipitation. And if we are talking of an arid climate, a dry region, then there are cases where ET accounts for about 90% of the precipitation. So the magnitude of ET can be very high, and almost in some cases entire precipitation, say except maybe 10-15%, entire precipitation goes back to the atmosphere. Now, another important thing to remember is that this is a process which links atmospheric science, hydrologic science, and agriculture science. Of course, forests also have important role here. At catchment scale, of course, ET represents the largest water flux after precipitation. Now, despite all this importance, it is very challenging to measure ET at catchment scales. And this challenge arises because of several reasons. One is that this is a process which cannot be seen by eye. We may be standing in a field, we may be feeling the water vapors going up, but we do not see them. So this is one reason that it's a variable which cannot be seen. Then it has a very heterogeneous behavior. ET depends on topography, it depends on land use, land cover condition, it depends on soil moisture, and so on. Now, since there are no methods, no easy methods to directly measure evapotranspiration, typically it is calculated by using the water balance equation. So we account for most of the terms or almost all the terms except ET, and the residual term of water balance is now our ET estimate. But I think all the delegates will know and they appreciate that this is not a very effective way of estimating ET, because the errors in different components are dumped into evapotranspiration, and that makes the estimates highly uncertain. So typically the way we estimate ET in most of the cases is that we estimate it as at a point scale. For example, we may use a evapotranspiration pan evaporimeter to measure the evaporation, multiply it by a suitable coefficient to convert the depth of evaporation into ET depending upon crop and other properties. There are a number of methods to estimate ET by using meteorological data. For example, Hargreaves-Samani method, Bland-Lakredal method, and so on. In late 90s, FAO carried out a detailed study of various methods to estimate evapotranspiration. And then they recommended that a method known as Penman-Montieth method that gives the best estimates of evapotranspiration by using meteorological data. And this method is of course called FAO 56, Penman-Montieth method. I'm sure that most of you will be familiar with this method. If not, this report FAO 56, which was co-authored by R.G. Allen and his colleagues, it is available freely on internet. Even if there is some difficulty, people can mail me and I can send this report. Now again, the limitation is, there are two limitations basically with FAO 56 Penman-Montieth method. One is that it gives a point estimate of ET, and second thing is this method requires a substantial amount of meteorological data, which is typically not available in Indian condition. So that makes this application of this method slightly difficult. Now, given this background, the remote sensing techniques are the ideal tools for application in the field of hydrology and assessment of evapotranspiration. And this assessment can be at a scale of a grid or a pixel. It can be at a scale of a sub-basin and even large basin. And these days, a lot of ET products are available, which make use of these estimation methods and provide us sometimes even global estimate. For example, there is a satellite called MODIS, and the data from MODIS satellite is being routinely used to estimate ET. Typically, the satellite-based methods, three methods are listed here. One is CBAL, which is surface energy balance algorithm for land. Another is the metric method, which is mapping evapotranspiration at high resolution with internal calibration. And then there is a method called SSEB. These methods incorporate complex formulations, assumptions, etc. for estimation of ET. And in the picture here, you can see a well-known method for estimation of evapotranspiration by using a device called lysimeter. So this here is a lysimeter installed in a large agriculture field. The conditions at lysimeter are identical to the field, and this can be very well used for estimation of ET. But installation of lysimeters and its operation is little difficult task, requires skilled manpower, requires finances, and our experience shows that it requires really dedicated manpower. It requires passion to install and operate a lysimeter. Now, this study had two objectives: to assess the variation of ET over a mountainous watershed and validate the assessment by using different methods. Well, friends, this year shows the location of our study area. So as I mentioned, it is a site in Uttarakhand. It is close to the Tehri Dam. I hope you can place the Tehri Dam on the map. This here is Uttarakhand map. And then this Hinwal River is flowing here. It is joined by another small tributary called Jijili. And together they pass through an outlet point where we are measuring discharge. The area of this watershed is about 102 square kilometer. This year shows the variation of altitude over the area. This area mostly receives precipitation in the liquid form or rainfall, and the annual average value is about 1200 millimeter. The upper part of the catchment, very small part, receives some snow during winter month, but it doesn't stay on ground for very long time. Climate is here generally humid, temperate. Forest is major land cover in both the catchments. When I say both the catchments, I mean the main Henwell catchment as well as Zilli catchment. Although the Henwell catchment has little less percentage of forested area, Jijili catchment is having high percentage of forest area. Agriculture is predominant activity here, where people grow rice and wheat. And this catchment has some social relevance in the sense that water is pumped from the catchment near the outlet to provide drinking water supply to about 87 nearby villages. Now, in terms of data, we used both remote sensing data as well as in situ meteorological data. So in terms of remote sensing, we had Landsat satellite images, and these images were downloaded and used for analysis. The period of imagery was from June 2016 to December 2018. A condition was that the images used should not have any cloud cover, because in presence of cloud, the data of thermal band becomes little, of poor quality, of less relevance. So it is very important that we choose the image which have absolutely no cloud cover. Then we also installed a number of instruments in the catchment to measure various meteorological data. And these data included temperature, precipitation, relative humidity, wind direction, net radiation, etc. And this meteorological data was used to compute ET by FAO 56 Penman-Montier method. Now, this here gives a picture of one advanced instrument that was installed in this site. So this here, what you see is a weather station, automatic weather station, which was installed in 2016. The instruments here are automatic weather station, which measures the parameters that I mentioned. Then we also have a what you call sonic anemometer, three-dimensional sonic anemometer and gas analyzer. This instrument you can see here on the left-hand side. It basically measures the transport of eddies in the vertical, horizontal, and Z direction, and it computes how much moisture and gases are going up and down. So that data can be used to estimate ET by what is known as the eddy covariance method. Then we had various types of data loggers. We also had a sensor called Cosmos, which measures the soil moisture by using cosmic rays. And this instrument provides an estimate of soil moisture over a radius of about 100-meter circle. Then there are evaporimeter pen, etc. So a lot of advanced instruments have been installed at this site to carry out measurement and then analyze the data to compute the various variables. Now the methods that were used to estimate ET, FAO56 Penman, modified Penman-Montieth method, then Hargreaves-Samani method, Priestley-Taylor method. For remote sensing data, we used two methods. One is CBAL, surface energy balance for land surface, and another is metric method. And later, of course, other methods like eddy covariance and pan-evaporimeter were also used to estimate ET. We are not going to discuss this part today. Now, I'm sure most of you will be familiar with FAO56 Penman, modified Penman-Montieth method. So this here is the equation to estimate ET at daily time step by using this method. This method can be used for both daily as well as hourly time steps. And the variables that are used were measured and were available with us. Now, this equation gives us what is called ET0. And to obtain the ET for a particular crop, the ET0 will be multiplied by a coefficient called crop coefficient. And this figure here shows how the crop coefficient varies with respect to time. So this is a typical variation shown here. Before that, this crop coefficient is basically the ratio of ET/PM for that crop and the ET0 value. So when the crop is planted, initially the crop coefficient is small because crops will be transpiring a small amount of water. But with the passage of time, as the crop grows, the crop coefficient also rises. It attains certain peak value, certain high value, and afterwards, when the crop is mature, it is getting ready for harvesting. The crop coefficient falls, and once the crop is harvested, it comes to 0. So this is the typical variation of Kc with respect to time. The values of Kc have been given by FAO56 for each crop in standard climatic conditions, but different agencies from countries across the world have also provided these coefficients for their condition. In this particular study, the equations, two equations which are listed here, they were used to compute Kc for various stages of the crop. Now, as I mentioned, we used two methods to compute ET by using remote sensing data. First method is what is known as surface energy balance algorithm for land, which was developed by a researcher named Wim Batsiansen in Netherlands. This method basically works on the principle of estimating residual energy. So what it does is it carries out energy balance for the region or for the place, and the equation is written here. So ET is the energy which is ET is computed by using the energy balance equation. So here Rn is the net radiation, incoming radiation, then G is the soil heat flux, H is the sensible energy. So these are subtracted from the net radiation to compute the energy left for ET. Now the beauty of this method is that there is a relationship between visible and thermal infrared spectral radiance of the area with a sufficiently large hydrologic contrast. And this contrast is in terms of dry pixels as well as wet pixels, or what is known as hot pixels and cold pixels. And this basically is the theoretical basis to compute ET. So this algorithm estimates spatial variation of these hydrometeorological parameters by using empirical methods. As far as field data is concerned, it requires only information of shortwave atmospheric transmission, shortwave surface temperature, and vegetation height. The method does not require any simulation model. It calculates fluxes independently from land cover, and it can handle thermal images at resolutions between a few meters to a few kilometers. So very large range is available here. Now, this method was proposed by Wim in somewhere mid-90s. Subsequently, in the beginning of 21st century, a group from USA led by Professor Richard Allen, the same person who developed FAO 56, he proposed this method, which is called metric method, or mapping evapotranspiration at high resolution with internalized calibration. So here the calibration process has been built into the model. This metric method is using the basic principles of Siebel, but it has some deviation, some improvement in the methodology. It departs from Siebel in use of weather-based reference ET to establish energy balance conditions at a cold pixel. As I mentioned that two types of pixels are identified, hot pixel and cold pixels. And then the calibration is carried out to determine the model parameter. This model does auto calibration for each image by using a reference evapotranspiration for a crop called alfalfa grass, which is denoted at ETR, and it is computed at hourly interval from weather data. Now, they have been able to establish the accuracy and dependability of ETR estimates by using the ET data from lysimetric measurements and other studies. These are some of the equations which are used for Siebel method as well as for metric method. Now, this here gives the flowchart of the algorithm of metric method. So you know that it derives a lot of vegetation indices from satellite data. I think you all must be familiar with the NDVI. Then SAVI is soil adjusted vegetation index. And then we have the DEM data, we have meteorological data. So using all this information, surface albedo, then radiation, etc., are calculated, and we have this ET estimates. Instantaneous estimates, which are converted to daily estimates of ET. I don't know why these funny lines are coming. Now, to estimate ET here, two extreme anchor pixels are identified. These are called cold pixels and hot pixels. And these are some conditions which should be satisfied for cold and hot pixels. So cold pixel should be fully vegetated area pixel, which is well watered, and ET is assumed to be maximum at these pixels. Then there are hot pixels or dry areas in the catchment where ET is assumed to be 0. In this study, a automatic selection method suggested by a group of people led by Bhattarai was used, and these pixels were identified. In this case, there was a, as we mentioned, we had a automatic weather station, and that place was devoid of vegetation. So that was chosen to be a hot pixel. Now, cold pixel represents well irrigated crop surface, and at these places, the ET is assumed to be slightly more than the ETR value, which is about 1.05 times ETR value. Then the authors, the waters, etc., they have mentioned that value of ET at hot pixels can be roughly estimated by using the data of past rainfall data. So if in the past 5 days, the rainfall variation is like this. If it is the rainfall at the rate of 15 mm or more has fallen in previous one day, then ET at hot pixel can be assumed to be 0.8 of ETR. If it is within 2 days, then 0.5 and so on. Now, this here shows some of the products derived from remote sensing data. So we have land surface albedo, we have NDVI, land surface temperature, net radiation maps, etc. And then instantaneous maps are generated by using this information, which is converted to daily values. These here are starting dates and finishing dates for various crops in the study area. And this data was collected from the information obtained from farmers. So both for rice crop, which is a kharif crop, rainfall season crop or monsoon crop, as well as wheat, which is winter crop or rabi season crop, these starting and end dates are given here. Now, this here shows a comparison of ET by using the metric method and ET by Penman-Montieth method. So in the upper diagram, you can see that there is a significant deviation between the two values. And then we tried to investigate the reason why we have this this deviation between the two values. And it was realized that we are assigning a zero value of ET at the hot pixel. And this might be the reason that we are not able to correctly compute the ET by using the metric method. So this deficiency was overcome. And finally, we can see in the lower graph that by removing this deficiency, a very good match between the ET estimated by FAO56 method and the metric method or modified metric method could be achieved. This here shows the improvement in a pictorial form with respect to dates. So you can see that in Kharif season, the blue squares, they represent the ET estimated by Penman-Montieth method. The black squares or black, you can say diagonals, they show the ET estimated by metric method. And there is a significant deviation between the two values. Then the red triangles show the ET estimated by modified metric method. And then we can see that the ET from this modified method is coming very close to the ET estimated by Penman-Montieth method. So the upper graph is for Kharif season. The lower graph is for the Rabi season with the similar notations. But here it is seen that even after incorporating the modification in the metric method, there is a significant deviation between the ET estimated by Penman-Montieth as well as by modified metric method. So it was concluded that the modified method is working well in the wet season, but it is not working that well in the dry season. This here is a comparison of statistical measures of performance. So we have overall data, and then we have the performance measures for individual seasons, Kharif seasons, as well as Rabi season. And this table also shows that the ET estimates by modified metric method show very huge improvement in the performance criteria for the Kharif season, while the improvement in Rabi season is not that significant. This year gives the spatial variability of the ET for different time periods. So finally, ET was estimated for a lesser Himalayan watershed. Lesser Himalayan means it is located in a region called Lesser Himalayas by using energy balance based method called metric method, which combines satellite data as well as meteorological data. The ET, it was found, is underestimated by using the metric method, especially for the Kharif season. So some improvements were incorporated in the metric method, and that led to better results for the wet season or for Kharif crop. However, the improvement in the winter crop or Rabi season were not that significant. This work was published in a journal called GeoCarto under the lead author of Dr. Manisha. This paper can be downloaded. Again, if you require this paper, please send a mail to me, my co-authors, and we'll be happy to share the paper with you. So, friends, that is all from me. I'll stop here. Thank you.
Thank you very much, Dr. Sharad Jain. It was an excellent presentation. India is, of course, an agriculture-based country, and such research work can really bring a lot of improvement and development in our key areas. Thank you very much, Dr. Jain.
Pleasure. I hope it was useful.
With this, we come to end of a very power-packed session. In this session, is there any more speakers?
No,
Shalini?
sir. No, sir. That was the last speaker.
That was the last presentation.
Yes, sir. It was the last presentation.
So we have come to end of a very power-packed session in which we had very interesting and informative talks covering a very, very wide range, right from river rejuvenation to sedimentation and water resources, then use of modern technology like artificial intelligence, deep learning, and things like that, machine learning in hydrology studies. Then we had last presentation by Dr. Jain covering the ET using remote sensing. So both the presentation content and quality of the PPT was excellent. Actually, I have seen there is a lot of demand for these PPTs, which I hope organizers will look into this. Thank you very much, all the speakers and audience. Thank you very much.
Thank you, sir.
Thank you.
It was a very nice presentation, and you have taken the area of the Himalayas and discussed about the rainfall and the agriculture, which is an important aspect when concerned with India. Thank you for the wonderful presentation. I would like to thank all the speakers for enlightening the research work to all the research scholars and the professionals. I hope in the near future their PPTs will be used for their as a reference by all the professionals and the research scholars. And many of the participants have even asked how to enroll in the doctoral program or in the MS program under the guidance of these speakers from in the respective institutes. So definitely, if the speakers won't have any objection, the organizers will provide the email. so that the candidates and the participants get in direct contact with them to work under their guidance in the near future. Thank you.
Yeah, we will be glad to provide. And actually, this presentation was prepared by my colleagues, led by Dr. Nema. So I'll talk to him. I hope he won't have any concern in sharing the presentation. We can provide the PDF of the presentation to the organizers.
Thank you, sir. Thank you. Ravi, sir, now I would like to.
I would like to thanks all the speakers today. They have enlightened us with a very detail about the water sources and application of remote sensing and GIS in various fields of hydrology, agriculture, and for the social fields also. So I think I would request Dr. Yadava to conclude, and we will be having the same timing tomorrow. And I am thankful to all the participants. There is overwhelming response, sir. Around 322 participants, they have joined from all over the world and listening this wonderful presentation by the eminent speakers all over the world. So I will request Dr. Yadava to speak and share his views with the participants.
Thank you, Dr. Ravi. First, let me thanks to Professor Verma, Chairman of this today technical session, who has accepted our invitation at short notice without any reservation. Sir, I am grateful to you for accepting our invitation and conducting this technical session.
Thank you very much, Dr. Yadav.
I am also thankful to all the speakers, those have spared their time, share their experiences and research activity with the participants, which are very beneficial and useful to them. And you will be receiving a lot of queries from them soon, because I am going to share their emails of all the speakers to all the participants. I'm also thankful to all the participants who attended at a very short notice and listened to the speakers patiently and raised their questions, queries for getting the necessary answer from them. Once again, I thank to all for giving their valuable time and having patience to listen everybody. Thank you so much. Tomorrow, again, we will be meeting at 17:30 hours. And tomorrow will be 6 speakers, 4 speakers from abroad, 2 from our country. And then we'll be having validatory function. Good night.
Good night, sir, and good night, everyone.
Dr. Daniel.